Good morning, Ananda. Good morning. So please kindly go through this question. Yeah. Go through this. See, a short transmission line has series impedance of R plus JX ohms. Okay. What is a load power factor? What is a load power factor? Load power factor value at which voltage regulation becomes zero. At which the voltage regulation value will become zero. See, first of all, what is a condition for zero voltage regulation? Approximately, yesterday we discussed that if the power factor angle is equals to 90° minus theta, power factor angle equals to 90° minus theta, at the time we get the what we call load power factor, sorry, voltage regulation value 0. So I'll write first condition for zero voltage regulation. Zero voltage regulation is phi r equals to 90° minus theta. But what is asking here? He is not asking about the condition, right? He is not asking about the condition. What is asking? Power factor, load power factor at that time means cos phi r. So load power factor, so I can say cos phi r, it will be like the cos of 90° minus theta. What is cos 90 minus theta? It will be sin theta. Cos 90 minus theta, it will be sin theta. So is it in leading or lagging? Definitely it will be in leading, because zero voltage regulation will occur only for leading power factor. Only for the leading power factor. Now, what is sin theta? Sin theta value. Please tell me. Yesterday we have seen in the what we call transmission line impedance triangle. Transmission line impedance triangle at some place, I think here. Yeah, transmission line impedance triangle. What is sin theta? We said x by mod z. So this value will come to be x by mod z. X by mod z means what? X by root of r square plus x square in terms of leading. So your answer will be D. Correct answer will be D, we can say. So I think all of you getting this one. X by mod z, else you can say x by root of r square plus x square. That is a power factor of load at which we are going to get the zero voltage regulation. Okay, let's take one more problem. One more problem I am taking up. See this. Yeah. Go through this question. See, a short transmission line has series impedance of 0 plus j0.4 per unit. Means resistance value 0, he said, and reactance value was 0.4 per unit. Okay. And it delivers 1 per unit current. It is delivering how much current? 1 per unit current. Yet 1 per unit receiving an voltage to an UPF load. For an UPF load, it is supplying 1 per unit current, right? The voltage regulation of the line in percentage is dash. Give up to 3 decimal points. Voltage regulation of the line is dash. Give up to 3 decimal points. Yeah, all of you stop writing. Stop writing. Just listen to me what I'm saying you. Just listen. See, if anybody asks you to calculate voltage regulation, just by giving some data like this, what is the formula for voltage regulation we should think? What is the formula for the voltage regulation we should think? All of you, please tell me. We should not think about percentage r cos phi r plus or minus percentage x into sin phi r. That we should not think. That's an approximate formula, right? That's an approximate formula. What is the original exact formula for the voltage regulation? That is modulus of Vs by A minus mod Vr by mod Vr. This is a original expression for the voltage regulation to be used all the time. Please kindly listen. Please kindly listen. Don't confuse with the thing what I am saying you. That percentage r cos phi r plus or minus percentage x into sin phi r is approximate formula. Again, you ask me, sir, why you are not using that formula and why you are using this formula? Why? It is the exact one. It's the exact one. That's why I'm using now. Okay. What is parameter A? What's parameter A? That is 1 because a line is a short line. The line is a short line. Line is short line. And moreover, he didn't mention about shunt element. He didn't mention about the shunt element. So line is a short line. So A value was 1, we can say. So you can write this like mod Vs minus mod Vr by mod Vr. Write it as mod Vs minus mod Vr by mod Vr. How much is receiving end voltage? He said. How much is the receiving end voltage? 1 per unit. Na? Receiving end voltage magnitude will be equals to 1 per unit. He said in the data. What about sending end voltage magnitude? What about the sending end voltage magnitude? Is there any possibility of calculating it? Is there any possibility of calculating that? What we call Vs value, sending end voltage? Yes. Yeah, we'll try. We'll try. We'll try. Just you see now, we have a short line with some series impedance. So like this, I am showing that series impedance is 0 plus j 0.4 in per unit form. Okay. And he said that we have a load at the receiving end side drawing a current of 1 per unit. So I'm showing some load here. So I'm showing some load here at the receiving end side. See, actually, this point will have a voltage of VR, load voltage, and this current is IR. See, current is 1 per unit in the sense its magnitude. Magnitude of the current equals to 1 per unit. So modulus of IR is 1 per unit, you mentioned. Receiving end voltage magnitude is also equals to 1 per unit. Clear? Receiving end voltage magnitude is also equals to 1 per unit. And what is the load power factor? 1. Cos phi r is unity. Cos phi r is 1. So now, listen. Our aim is to calculate the source voltage, na? Or sending end voltage, you can say. Our aim is to calculate the sending end voltage, Vs. Let. This VR is taken as reference. Let VR is taken as reference means you can call it as 1 at an angle 0 degree. Chosen as reference. Then how is it IR current? I can say IR current. Magnitude will be 1. Magnitude will be 1. How much is the angle? This power factor angle is 0 degree. Cos inverse 1. Cos inverse 1, that will be 0 degree. So obviously this current is also of 0 degree angle only. Because power factor is 1. So voltage and currents at the receiving end side are in phase. In phase. So 1 at an angle 0, 1 at an angle 0. Now you apply KVL for this loop and you try to find out the sending end voltage. So KVL for loop, it will give the sending end voltage Vs. What you can say Vs here? That is nothing but VR plus IR into Z. VR plus IR into Z. So what is VR? 1 at an angle 0. What is IR current? Also 1 at an angle 0. What is Z? J 0.4. So it will come to be 1 plus J 0.4. 1 plus J 0.4 per unit. Clear? 1 plus J 0.4. And you take only magnitude of the sending end voltage. That will be sufficient for this calculation or the requirement. So I can say sending end voltage magnitude here. Sending end voltage magnitude mod Vs, which is nothing but square root of 1 square plus 0.4 square. 1 square plus 0.4 square. I think you may get this number like 1.0707 per unit. 1.0707 per unit. 077 are you getting? Okay. 077 per unit. Check once again. 1.077 per unit. Okay. So after getting this mod Vs, now you can say the voltage regulation here, which will be mod Vs value minus mod VR value 1 by mod VR multiplied with 100%. So it will come with a number like 7.7%. It will be like 7.7% as a voltage regulation. 7.7% as a voltage regulation. That's the answer what we have to fill in the blank. So the answer we have to fill in the blank. Let's look back to the question. He's asking in percentage. Na? Asking in percentage means you have to give for 3 decimals. Kindly tell me this number for 3 decimals. How much? Tell me this number for 3 decimals. 7.7032. 032. 032. 032. So answer will be 7.703. Answer will be 7.703. We have to fill in the blank. Fine. Fine. So this is one way of asking the question. For example, same question. I will show in the next slide. I'll show in the next slide. Same question I am copying whatever I have shown earlier. Yeah, this one. So a short transmission line has series impedance. Like this. The load power factor is unity. In bracket, cos pi r is equals to 1. The voltage regulation of the line in percentage is how much? Tell me for this question. What's your answer for this question? See, again, this problem, as if he is asking voltage regulation, we should make an attempt to find out the voltage regulation by using the original formula for short line, like mod Vs minus mod Vr by mod Vr. Mod Vs minus mod Vr by mod Vr. But there is no clarity. There is no clarity regarding what is the value of receiving end voltage and what's the value of sending end voltage. Na? There is no clarity. There is no clarity regarding what's the value of mod Vr and what's the value of mod Vs. And is it possible to find out these numbers, sending end voltage and receiving end voltage? No. So here you write, in this problem, it's not possible to find, it's not possible to know the values of mod Vs and mod Vr. The values of mod Vs and mod Vr. So I can say the voltage regulation here approximately percentage r cos pi r plus or minus percentage x into sin pi r. This equation we have to use now. There is no other choice. There is no other choice. Clear? So this, if you attempt to calculate, percentage r is 0 into cos pi r 1, okay, plus let's say x value, percentage x is 40%, 40%. Sin pi r is 0, na? Cos pi r is 1 means sin pi r will be 0, and this number will come to be 0%. All of you getting when to use original formula and when to use approximate formula. Approximate formula when we have to use if there is a lack of data, there is insufficiency in the data. If you said only impedance, power factor, ask it to find voltage regulation, use approximate formula. But if you provided some more data, then you have to go with analysis of KVL and you have to find out the voltage regulation number. All of you getting this? Please tell me. Yeah, fine. So let's take one more problem quickly on this short transmission line analysis. So I'm taking one more problem. Check this. This one. A short transmission line has series impedance of 0.06 plus J0.12 per unit. What is the value of voltage regulation possible at rated load with leading power factor? At rated load with leading power factor. Kindly observe it. Short transmission line has a series impedance of 0.06 plus J0.12 per unit. What is the value of the voltage regulation possible at rated load with leading power factor? Is it possible to find out voltage regulation value? No, because he didn't give what is the value of power factor, right? See, for example, if he has given how much is a power factor value leading, I might be using an expression like percentage r cos pi r minus percentage x into sin pi r. I will substitute the values and I will try to get it. Okay, but he didn't said what is the value of the power factor. He didn't set the value of the power factor. But you see, if you look at the voltage regulation curve, approximate voltage regulation curve, what we have plotted, just look back. This one. This is a voltage regulation curve we have plotted. See, this is a side of leading, right? Just listen to my words, please. This is a side of leading, na? This is a leading side. From 0 degree to 90 degree leading. Okay. In this span of angle, voltage regulation is in this manner. Voltage regulation value. But you observe that that voltage regulation value always less than percentage R, right? For that leading power factor condition, voltage regulation is always less than percentage resistance. All of you understood this? So either the value may be positive, negative, or zero, whatever it is, it will be less than percentage R at what condition? Rated loading conditions only. Only at the rated loading conditions from the voltage regulation curve. Yeah. So let me write in the solution. From voltage regulation curve. See, for leading loads, always voltage regulation will be less than percentage resistance. Voltage regulation will be less than percentage resistance. Okay? Yeah, check that. Voltage regulation will be less than percentage resistance. If you want, you see from the data given, percentage resistance value 6% you have, 0.06 he said. Percentage reactance value was 12%. Percentage R 6%, percentage X is 12%. So obviously for leading loads, voltage regulation will be less than percentage R, means it will be less than 6% at rated conditions. Right here, at rated conditions. So it will be less than 6%, means obviously we should go with the answer of 3% here. Okay. So I'll say 3% is a suitable one. 3% is a suitable one. So I'm showing the options, whatever they have given here. A, B, C, D. So this 3% occurs at leading load. Okay, could you please tell me when the 6% will occur? Could you please tell me when the 6% is going to occur? Anybody? When 6% will occur? At UPF. At unity power factor, definitely we are going to get the voltage regulation equals to percentage R, right? That will be equals to 6%. Occurs for UPF load. Occurs at UPF load. Okay, 12%. 12% when it's going to happen. 12%. Anybody? 12%. Yeah, 12%. When it's going to happen? 12% it's for lagging load. That's okay. Lagging load. How much? How much lagging you can say? That will be 0 power factor lagging. 0 power factor lagging. Just you observe. 90 degree is giving percentage X na. So 12%. 90 degree power factor angle means cos 90. 0. So it will be 0 power factor lagging condition. Occurs at 0 power factor lagging condition. Lagging load. Okay, when 18% is going to occur, when we are going to get the voltage regulation as 18%. When? So it may not be possible. It may not be possible to get the voltage regulation as 18%. Why it is so means, for example, if we calculate the percentage Z value from this one, which is a maximum voltage regulation we feel, we are feeling, percentage mod Z, if you calculate, it will be square root 6% plus 12%. How much is this number? Anybody? Root of 6% square plus 12% square. So it will be 13.41%. See, maximum voltage regulation itself possibly is 13.41%, but he is asking us to go with 18%. 18%, it is not possible. So it's not possible at rated conditions. Rated or full load conditions. not possible at the rated conditions. Not possible at rated conditions. Sir, ZPF only occurs only in leading power factor. Yeah, ZPF means zero power factor. That's it. Zero power factor. It may be in lagging or leading. Yeah, it may be either in lagging or leading. Doesn't matter, whatever it is. Yeah. So I think you are clear about this one. So by this problem, what I want to tell here is for leading loads, voltage regulation will be less than percentage R. For lagging loads, voltage regulation will be greater than percentage R. Greater than percentage R. Okay, done. So let's move with the next topic, that is medium transmission line analysis. For ZPF leading, voltage regulation will be negative of the percentage X. Negative of the percentage X means it will be minus 12%. Minus 12%. Yeah. So let's continue. Let's continue with the next topic, that is medium transmission line analysis. Medium transmission line analysis. Yeah. Medium transmission line analysis. See, in this medium transmission line, we mentioned that we have different models of construction. First, we said receiving end capacitor model. Next, sending end capacitor model. Then nominal P, nominal pi, like that. So I'll take up each and every model and we'll find out the ABCD parameters. Okay? Yeah. Let me take first one. First model, that is receiving end capacitor model. Receiving end capacitor model. Or load end capacitor model. Like that also you can call here. Load end capacitor model. Like that also you can call. Receiving end capacitor model, or you can say load end capacitor model. Yeah, let me show that model here. Let me show that model. Answer already we mentioned, right? Answer is D. For leading load, he is asking. Okay, fine. See, I am showing this model already we have done in the equivalent circuits. So this is that receiving end capacitor model, and it's a sending end side. We have VS and IS here. And it was a receiving end side, it is VR and IR. VR and IR. Okay. So RLC we have, RLC. And already we said for the flexibility in the analysis, for the easiness in the calculations, series element we keep in the form of impedance. Shunt element we are going to keep in the form of admittance. Series element we keep in the form of impedance. Shunt element we are going to keep in the form of admittance. Okay. What is series impedance of line? Series impedance of line. Series impedance of line, Z is equals to R plus J omega L. Series impedance is equals to R plus J omega L. Else you can call it as R plus JXL also. R plus JXL. Next, shunt admittance. Shunt admittance. Y you can say here. Y. That will be inverse of that capacitive impedance, right? So it will be 1 by minus JXC. 1 by minus JXC. So 1 by minus JXC in the sense, it will come to be J omega C, because XC is 1 by omega C, and it will turn to be J omega C. Else you write this one JB. JB. What is that B name? Susceptance. Shunt susceptance of the transmission line. B is the shunt susceptance of transmission line. Susceptance of transmission line. B is the shunt susceptance of the transmission line. Okay. So now, first and foremost, we have to find out ABCD parameters of this one. We have to find out the ABCD parameters of this one. To calculate ABCD parameters, we have two techniques. One, applying KVL, KCL, and find the relation between sending end quantities to receiving end quantities. It will give ABCD. That's one method. Other method is going with a cascade connection. See, I have two parts of network, I can say. One is a series branch, next one is a shunt branch. What is a series branch ABCD? What are the series branch ABCD? 1Z01. Shunt branch ABCD. 10Y1. And as these two are in cascade, multiply the two ABCD parameters together. That will give you resultant ABCD of the receiving end capacitor model. Okay. Yeah. So I will show here in the next slide. ABCD parameters. ABCD parameters. So first branch, it will be 1Z01. Second branch, it will be 10Y1. You multiply these two ABCD, it will come to be 1 plus Z by ZY1. 1 plus Z by ZY and then 1. These are the ABCD. Now, you can see A and D values. A and D unequal. Network is unsymmetrical. That you know already. Just by looking at the receiving and capacitor model itself, you can say it is unsymmetrical one. So A and D are unequal. Network is unsymmetrical. Network is unsymmetrical one. But what about the value of AD minus BC? That's 1. AD minus BC value was 1. You can say network is reciprocal. Network is reciprocal. Network is reciprocal. Okay, next thing. What is the expression for the voltage regulation? What is the expression for the voltage regulation? You write the original one. You write the basic or exact equation for the voltage regulation. Here, you know it is modulus of Vs by A minus mod Vr by mod Vr. So you'll get the voltage regulation like modulus of Vs by A minus mod Vr by mod Vr. And what is no load voltage of transmission line here? No load voltage of line is Vs by A. That's it. No load voltage of transmission line VR0 is equal to Vs by A. No load voltage of the transmission line VR0 is equals to Vs by A. Okay, fine. Next thing, listen. How is the parameter A? Equation I said already 1 plus Z by. That's okay. Equation I said already 1 plus Z by. My question is, how that number will come? Is it coming as more than 1 or less than 1? Will the parameter A value, magnitude, will it come more than 1 or less than 1? That we have to know. See, for a practical transmission line of certain length, I will be taking up some resistance, inductive reactance and capacitive reactance values as we are doing earlier. That we will use to calculate the parameter A. Then we will make the comment. Okay, let's move to next slide. Try to understand this. For example, we have a line of length 150 kilometers. Line of length 150 kilometers. Series resistance value, I'll say 20 ohms. Don't bother about it. I'm giving some numbers. Moreover, these numbers are a bit close to the practical values. Okay, 20 ohms. Series inductive reactance, I'm saying XL, 50 ohms. Series inductive reactance is 50 ohms. Shunt capacitive reactance, I'm saying shunt capacitive reactance, let's say 2500 ohms. Shunt capacitive reactance, I am taking like 2500 ohms. Very simple. From these things, can you tell me what is series impedance of line? Series impedance of transmission line means it will be simply R plus JXL. You can write. So R value 20 plus JXL means it is 50. So it will be 20 plus J 50 ohms you can get. 20 plus J 50 ohms you are going to get as a series impedance of that transmission line of 150 kilometers. Next one. Shunt admittance of line. Shunt admittance of line is 1 by minus JXC. Means you'll get this like 1 by minus J 2500. 2500. Yeah, you please tell me this value how much? 1 by 2500. So it will be like 4 into 10 power minus 4 J. 4 into 10 power minus 4 mho. J 4 into 10 power minus 4 mho. See, this is a way how you have to understand. Just listen. Don't confuse. All of you stop writing. All of you stop writing. Just listen. Just listen here. We are seeing some transmission line on the tower. 150 kilometers length of line we are seeing on the tower. For that line, we calculated 150 kilometers length resistance value, 150 kilometer length inductive reactance, 150 kilometers capacitive reactance. Okay, by that, I got the series impedance for 150 kilometers length, shunt admittance for 150 kilometers length. See, while I am drawing the equivalent circuit of that on the paper, look my words, please. While I am drawing the equivalent circuit of that line what we are seeing on the tower, we are drawing that on the paper. I am keeping total series impedance at only one place like this, and total shunt admittance at only one place in this manner. Who is saying this model to us? Is it transmission line, or we ourselves are taking this model? Is it the model given by the practical transmission line, or we are taking this model? Ourselves, we are taking that model. Transmission line is not saying anything about this model. Yes or no? Line is not saying anything about this model. See, if anybody asks you to draw transmission line equivalent circuit, just to draw simply like this. This is a transmission line. That's it. Now, if they ask you how to draw it approximately, how to show series impedance, shunt admittance, then you show some model, whatever you want. Okay. See, by arranging that Z and Y in that manner, the parameter A value I am getting like 1 plus ZY. That A value we are calculating. So parameter A is 1 plus ZY. So it will come 1 plus Z. 20 plus J50. J4 into 10 power minus 4. Yeah. See, use a calculator. Use a calculator. We are at the learning stage. Use a calculator and find out this number. Maybe in your GATE examination, they may not give laborious problems doing with the calculator. But while you are learning the things without using calculator, learning the things is a bit difficult. It's not possible to learn the things. Okay. Use a calculator as we are in the learning stage. Use it. Use it and tell me how much is that. How much is that parameter A, magnitude and angle? 1 plus Z, Y. So this magnitude will come 0.98, I think. Angle will be around 0.47 degrees. No units. 0.98 is our magnitude and angle is 0.47 degrees approximately. See, one observation here is modulus of A number is less than 1. That's for sure. Modulus of A number is less than 1. Mod A is less than 1. Not only that, we mentioned that VR0 equals to Vs by A. Na? Mod VR0, you can say modulus of Vs by A. Modulus of Vs by A. See, from these two things, what we can comment here, this magnitude of A is less than 1. If that magnitude of A is less than 1, definitely mod VR0 value will come greater compared to mod Vs. Mod VR0 value will be definitely greater compared to mod Vs. So no load receiving end voltage of transmission line. No load receiving end voltage of transmission line looks in higher compared to sending end voltage. So under no load operation, receiving end voltage magnitude is greater compared to sending end voltage. This phenomena we are going to call it as Ferranti effect. This phenomena we call as Ferranti effect. So Ferranti effect represents the rise in the receiving end voltage under no load condition with respect to sending end side. Right? So I'll write simply Ferranti effect means Ferranti effect means it's a condition. It's a condition where the receiving end voltage magnitude comes higher than the sending end voltage magnitude. Sending end voltage magnitude. Right? So it's a condition where the receiving end voltage magnitude comes higher than the sending end voltage magnitude. Sending end voltage magnitude. So when it's going to occur, one thing, it's under no load condition. It may happen. Next one, under lightly loaded condition, less loading conditions. So it occurs at no load condition and light loading conditions. Lightly loaded conditions on the transmission line. Conditions on transmission line. Lightly loaded conditions on the transmission line. Yeah. So you please complete this one quickly. So next, of course, it's not the end of the Ferranti. I will be continuing this one each and every time. So after this, we'll discuss about the sending and capacitor model. Sending and capacitor model. So I'm showing previous slide. If anybody is still doing it, please complete the previous slide. Yeah, it may be Shiva, maybe. Yeah. So next heading is sending and capacitor model. Sending and capacitor model. Sending and capacitor model. So we'll be keeping the total capacitance of transmission line wire at the sending end side. We are concentrating, or we are going to lump. We are going to lump the total capacitance at the sending end side. Like this, we can say. And this is the sending end side, Vs we have. And it's a receiving end side, it will be of VR. Yeah. So next you see, this RL series branch will have an impedance of Z. Shunt branch will have an admittance of Y, as it is we have taken earlier. Okay, straightly you go for ABCD parameters calculation of this one. Two branches, shunt branch, next is series branch. So take up ABCD of branch 1, branch 2, multiply. ABCD parameters of this will come like, first shunt branch ABCD 10Y1. Next series branch ABCD will be 1Z01. 10Y1. Next one is 1Z01. Yeah. So if you multiply these ABCD parameters, you will get like 1ZY 1 plus ZY. You get like 1ZY 1 plus ZY. A and D are unequal. Definitely network is unsymmetrical. Unsymmetrical network. And the value AD minus BC, that's 1. Network is reciprocal, definitely. It is unsymmetrical, but it is reciprocal. Unsymmetrical network, and it is reciprocal. Yesterday we have discussed about it. Yesterday we have discussed about ABCD parameters, how to write for each branch. Yesterday we have discussed about the ABCD. Yeah, so let's continue now. Let's continue. What is a voltage regulation formula? voltage regulation formula you can take. So original formula is like mod Vs by A minus mod Vr by mod Vr. Mod Vs by A minus mod Vr by mod Vr. What is the parameter A? Parameter A is 1, na? So parameter A is 1 means it will come to be mod Vs minus mod Vr by mod Vr. Parameter A value 1. So it will be mod Vs minus mod Vr by mod Vr. And what is the no load voltage of transmission line? Vr0. No load voltage of transmission line Vr0, which is equals to Vs by A. A is equals to 1. And you can get Vr0 equals to Vs. No load voltage of transmission line Vr0 is equals to Vs by A. And parameter A is 1, as we said earlier. So I can call this mod Vr0 value is equals to mod Vs. No load receiving end voltage of transmission line mod Vr0 is equals to sending end voltage as mod Vs. Sending end voltage mod Vs. Clear? Do you have any Ferrand effect in this model? Do you have any Ferrand effect in this model? No. See, the statement what you should say exactly is statement. Listen please. The statement what you should say exactly is there is no Ferrand effect represented in this model. Represented in this model. That does not mean that the line will not have any Ferrand effect. Practical line might have Ferrand effect. Practical transmission line might be having Ferrand effect, but we are unable to show that in this model, what we have taken on the paper. Okay, so no Ferranti effect. No Ferranti effect. Ferranti effect represented in the sending end capacitor model. Sending end capacitor model. No Ferrand effect was represented in the sending end capacitor model. Sending end capacitor model. Under no load condition, there is no voltage drop. Under no load condition, there is no voltage drop in the series impedance. Because under no load condition, we don't have any current flow in the RL circuit. Okay, now the question is, who is the cause for the Ferrand effect generally? Why voltages are written in modulus? See, Malavika, we want to check only voltage magnitude rise. Voltage magnitude rise, only we have to check. Always positive only. Magnitude of voltage we are considering. Yeah. Please listen to me. Who is the cause for the Ferrand? Is it inductor or capacitor? Is it inductor or capacitor? Cause for the Ferrand. Okay, let me take one example here. One example. I'm giving some number of circuits here, number of circuits with L and C. Check which circuit exhibits the Ferrand effect, which circuit will not exhibit the Ferrand effect. Based on that one, we'll come to know who is the cause for the Ferrand effect in the two elements L and C. Okay, yeah. So I will say first one, inductor. Okay, second one, capacitor, only capacitor. Third one, both L and C I have shown. Both L and C. Fourth circuit, again here also both L and C. Like this. Make it quick. I am writing these things quickly. Just look here. All are having sending end voltage same Vs. All are having the sending end voltage as Vs. Vs. All are operating under no load condition. All the circuits are operating under no load condition, means output current is 0. Output current is 0. Output current is 0. Okay, next, listen here, listen. What is this no load voltage of this circuit, VR0? What is the no load voltage of that circuit? Anybody tell me please, VR0 how much? VR0. That will be Vs. That will be equals to simply Vs, because no voltage drop here, sending end and receiving end voltage are equal. What is VR0 here? Anybody? What is VR0 in this case? See, this node voltage, both are same, na? This node and this node will have same voltage. That will be same as Vs, right? That will be same as Vs. Okay, no change in the voltage, even though you have a capacitor. Even though you have a capacitor. Okay, next thing. What is this voltage? What is this voltage VR0? How much is that? Is it Vs? Is it Vs? Yes. This value is also equals to Vs. And what is this voltage? What is this voltage? This VR0 might be greater compared to Vs in magnitude, definitely. This VR0 magnitude will be greater compared to Vs. Following all of you? Right. Now you please tell me, who is the cause for the Ferrand effect? Is it inductor or capacitor or both? See, if you are in an impression that only capacitor is the reason for Ferrand effect, only capacitor is the reason for Ferrand effect, network 2 should show the Ferrand effect, right? Network 2 should show the Ferrand effect, but it's not showing. So if you are feeling that only inductor is a reason for Ferrand effect, network 1 should show that. It's not showing. See, network 4 is showing the Ferrand effect, where we have both L and C elements. We have both L and C elements. Means the comment what we have to make here is, right, to show the Ferrand effect in the network, or to exhibit the Ferrand effect in the network, both L and C elements should exist in the model. Both L and C elements should exist in the model. Okay, so I'll write that statement. To exhibit the Ferrand effect, exhibit the Ferrand effect in the equivalent circuit or in the model, the transmission line model. Both L and C should exist in the model. Should exist in the model. Both L and C should exist in the model. But you see that the third circuit is having both L and C, but it's not showing any Ferrand effect. This keeping L and C is not sufficient. Keeping L and C is not sufficient. Okay? Keeping L and C is not sufficient. There should be one condition. What is that condition? You see, this is carrying some charging current IC and this is carrying some charging current IC. Whether that IC is flowing through inductor? No, IC is not flowing through inductor. But this IC, what you have shown here by the application of KCL, is passing through inductor. Means keeping L and C is not sufficient. Keeping L and C is not sufficient. We should arrange them in the circuit. We should arrange them in the circuit in such a way that whatever the charging current we have, so-called capacitor current, whatever the charging current we have, that should pass through inductor. That should pass through inductor. Okay, so I can say here, provided that charging current, or you can say capacitor current, will pass through inductor. Will pass through inductor. So I think all of you getting this one. So figure third, like no inductor present due to open circuit, but should both present. Yes, Shahil, both are there. Both L and C are there, but this IC is not flowing through inductor, right? IC is not flowing through inductor. So 0 voltage drop. This node voltage, same as V's. Okay, listen here now. Listen here. See, all of you understood what I am doing here exactly? All of you understood this, what I am doing? Practically speaking, listen to this word. Practically speaking, transmission line, what we are seeing on the tower is having Ferrand effect. Practically speaking, line what we are seeing on the tower is having Ferrand effect. That we should show in the circuit. For that purpose, we should keep both L and C elements, but whatever the capacitor current we have under no load, it should pass through inductor. At least in some portion of inductor, it should pass. Then only that circuit what we have constructed will show the current. Okay. But in general, if anybody asks you, who is the cause for Ferrand effect means, you can say simply line charging current. In the sense, charging current passing through the line. Charging current passing through the line means passing through the inductor or passing through the reactor. That's it. Okay. So Ferrand effect caused by practically Ferrand effect caused by line charging current. Is a charging current passing through line, else you can say charging current passing through inductor of the line. So how in fourth case we are getting VR0 more than Vs? That's what we have explained in the receiving end capacitor model. Okay. Yeah. So done. Next, let me take nominal T and nominal pi models quickly. Nominal T, nominal pi. Next model we are going to take up here. Third one, nominal T model. Right. Representation of transmission line in the nominal T. Representation of transmission line in the nominal T. Yeah. So I'll show that model. Already we have drawn. Is R by 2 L by 2. And it's again R by 2 L by 2 we have. And it is a total shunt element capacitor at one place, I can say. Right. So R by 2 L by 2. R by 2 L by 2. And this is sending end side. You can call it is Vs. And it's a receiving end side. You can call it is VR. See this R by 2 L by 2. R by 2 L by 2 combination, we name this as Z by 2. And this will be again Z by 2. And this is Y. Shunt element Y. Okay, now you try to find out ABCD parameters. First you take for Z by 2, next Y for Z by 2, and you multiply all the three matrices, you will get the resultant ABCD. So you can get the ABCD parameters of this network with cascade connection. 1 Z by 2 0 1, 1 0 Y1, 1 Z by 2 0 1. 1 Z by 2 0 1, 1 0 Y1, 1 Z by 2 0 1. Okay. So if you multiply these three, matrices, you will be getting ABCD like 1 plus ZY by 2, Z into 1 plus ZY by 4, Y, and you have 1 plus ZY by 2. 1 plus ZY by 2, Z into 1 plus ZY by 4, and you have Y, 1 plus ZY by 2. Parameters A and D are equal. Network is symmetrical. Network. And if you calculate the value AD minus BC, that's 1. Network is reciprocal. AD minus BC, if we calculate, that will be 1. Right? Network is reciprocal. Fine. Let's calculate for nominal pi also in the same sequence. Then we will make comment on nominal T and nominal pi. Okay. Yeah. Let's take in the next slide. Nominal pi model. nominal pi model. Please complete it quickly. I will wait for 10 seconds. Please complete it quickly. Sir, can you please tell how you are writing these matrices? Yesterday we discussed it, right? Mukesh, have you attended yesterday class? Yeah. Yesterday we have discussed about that, how to write those ABCD, all those things. That's correct only. Z into 1 plus ZY by 4. That's correct. That B matrix. B matrix, B term is correct. Just you cross check once again if you want. B number. It's 1 by 4 only. Rhythm, it is 1 by 4. 1 by 4. Z into 1 plus ZY by 4. That's it. Yeah. So let's continue with the nominal pi model. Nominal pi model. Nominal pi model of line. Nominal pi model of line. Right. So I can say like this. This equivalent circuit already we have drawn. So C by 2 I have to show on these sides. C by 2 and this is RL. Sending end side VS and you have receiving end side as VR. Next, see this total impedance, you know, it is Z and this will be admittance. Admittance, it will come to be Y by 2. It will come to be Y by 2. It will come to be Y by 2 and this will be again Y by 2. Pandey, kindly check the thing. Kindly recalculate. Okay. It's not whole by 4. It's not whole by 4. 1 plus ZY by 4 whole multiplied with Z. Yeah. So you take up the ABCD of this one. ABCD of this one. ABCD of this one. First, for the shunt element Y by 2. Shunt element Y by 2. 1, 0. Y by 2, 1. See, in the previous class, we discussed about one problem. We discussed one problem in the pi model where I said this element is minus J to XC. That's okay. This element is minus J to XC and this will be minus J to XC. But if you go with admittance, it will become half. If you go with admittance, it will become half. Okay. So next, I can say in the next slide, it is 1Z01. So next matrix 1Z01. Next matrix will be 10 Y by 2, 1. 10 Y by 2, 1. So if you take up this multiplication of these 4 matrices, you will be getting like 1 plus ZY by 2, Z, Y into 1 plus ZY by 4. Okay. And you have 1 plus ZY by 2. Like this, you can say. Like this, you will get the matrix. Yeah, you have to remember these matrices, Rawat, particularly for ESC prelims examination. Just they are asking these elements also. For example, in nominal pi model, which of the following represents the parameter C? Nominal T model, which of the following parameters represents B? Like that, they are asking some simple questions in ESC prelims. For that purpose, you have to remember. Even for gate examination also, you have to remember these ABCD elements. Very easy to remember, I will tell you. Very easy to remember. Just look at this one. First, let me write A equals to D. Network is symmetrical. Network is symmetrical. and the value AD minus BC is 1 and it is reciprocal. Network is reciprocal. Network is reciprocal. Yeah. Please listen here. Please listen. See, parameters A and D are equal. Parameters A and D are equal. That's 1 plus ZY by 2 in both cases. Observe. 1 plus ZY by 2, 1 plus ZY by 2. Here also. 1 plus ZY by 2, 1 plus ZY by 2. Done. Listen here. Listen. Rawat, listen here. Nominal T, total admittance is at only one place. Total admittance is at only one place, shunt. So parameter C equals to Y. Parameter C equals to Y. C is representing shunt admittance, right? Y. B represents series impedance. So it becomes Z into 1 plus ZY by 4. Z into 1 plus ZY by 4. Nominal pi. Total series impedance is at only one place. Total series impedance is at only one place. B equal to Z. B equal to Z. And what is C? C representing shunt admittance. It will come Y into 1 plus ZY by 4. Y into 1 plus ZY by 4. 1 plus ZY by 4 you remember as a factor of multiplication. 1 plus ZY by 4 you remember as a factor of multiplication in this as well as in the previous. Okay, so that's the way how we have to remember the things. Okay, yeah. Let's continue to check how is the parameter A in both models, because both models are having same value of A 1 plus ZY by 2, and we try to calculate that number with the Z and Y values what they have given, what we have taken up. Okay, yeah. So let's proceed with the same example calculation. Let's proceed with the same example calculation. Length of line 150 kilometers. Okay, 150 kilometers. Series Z means series impedance. We have taken 20 plus J 50 ohms. Shunt admittance we have taken, it is J4 into 10 power minus 4 more. After getting this Z and Y, if you are arranging these values of Z and Y in the nominality or nominal pi model, parameter A is coming like 1 plus ZY by 2. So it will come 1 plus Z Y by 2. Yeah, you please calculate this number and kindly cross check. Will this number is coming more than 1 or less than 1? Please kindly cross check this. So this will come like yeah. Tell me how much is this magnitude and angle? Less than 1 you are getting? Close to 0.9999 somebody is saying me. 1 plus ZY by 2. So you'll get 0.99. Okay, 0.99. That's it. Angle 0.23 degrees. 0.23 degrees. Okay, listen. Again, you observe that modulus of A is less than 1. Modulus of A is less than 1. As modulus of A is less than 1, definitely no load receiving end voltage magnitude will be greater compared to sending end voltage magnitude. So you write as mod A is less than 1 and mod VR0 is equal to modulus of Vs by A. I can write VR0 is greater compared to Vs in magnitude. So the Ferrand effect was represented. Ferrand effect was represented in both nominality and nominal pi modes. Therefore, Ferrand effect exists in both nominality and nominal pi models. Nominality and nominal. Yeah, see, without doing this calculation of A, can we tell? Without doing this calculation of A, can we tell parent effect is exhibited in these two models? Without doing these calculations. Yes or no? Yes. Because you see here, under no load condition particularly, whatever this half of the capacitor current you have, whatever the half of capacitor current you have, that will flow through this impedance, right? Half of the capacitor current what you have, that will flow through this impedance. So the condition what I said, charging current should pass through inductor. Maybe some portion of charging current passing through inductor, sufficient. In the previous case, this is a charging current total passing through L by 2. That also shows the current effect. Okay, so without doing calculations also, we can say. Yeah. Next, let's continue with this. Sir should have to check for A always or directly by charging current. Yeah, any method you can follow, Ramakrishna. Any method you can follow, Ramakrishna. That's your wish. Yeah. Let me continue now. Let me continue. Check connections already we have taken. What you have doubt in this subject? Okay, fine. Why, sir? Why is not clear? Why is? Physical meaning of charging current from day before yesterday we are explaining. Again, if you want Ankur, you ask me in doubt session. I will explain about the charging current. Okay, Ankur. Mic sometimes goes down. Okay, fine. I will try to rectify it. If possible. Okay, next. See, we have discussed about 5 models per line till now. 5 models for the transmission line till now. What are the 5 models? Short line model, receiving end capacitor model, sending end capacitor model, nominality, nominal pi. 5 models we have discussed till now. In these 5 models, which model shows highest Ferrand effect? Which model shows the highest Ferrand effect? Means whichever the model is having lowest mod A value, that will show the highest Ferrand effect, can I say? If the modulus of A is lowest number, then we can say VR0 is rising to a high value compared to Vs. Okay, see, if you check that modulus of A values, first for short line, what is mod A? For short transmission line, what is modulus of A? 1. Modulus of A is 1 for short line. Receiving end capacitor model, you got some number 0.98. Sending end capacitor model 1. Nominality, nominal pi, both are having a number like 0.99. So compared to all, receiving end capacitor model is having lowest mod A. Receiving end capacitor model has the lowest mod A. So it shows highest Ferrand effect compared to any other model of the line representation. Okay, so I am saying the statement here. Receiving end capacitor model shows the highest Ferrand effect compared to all other models of line representation. Line representation. Compared to all other models of line representation, receiving end model is going to show the highest Ferrand effect. Yeah, okay. Exact Ferrand effect will be represented by long transmission line only. Vishnu, always if you say which is exact, long line, that's it. There is no other answer. Okay. So next, I will discuss a little bit about the what we call this nominal pi model. Just try to understand what I am saying. Look here. Look here, a small heading. Avoiding Ferrand effect, I will say. Avoiding Ferrand effect. How to avoid? Okay. How to avoid the Ferrand effect. That's the meaning. Nominal pi model I am taking because there's a bit appropriate model with respect to long transmission line. That's why I am taking only nominal pi model. So it is a series impedance of line Z. Series impedance of line Z. And we have admittance of line here. Tells better I will neglect the resistance. I neglected the resistance. Taken only series inductive reactance for time being. For easiness in the analysis. This is JX line. Kindly follow it. Kindly follow it. JX line. Series impedance. Pi model. Transmission line. This is JB line by 2. Is it okay? JB line by 2. JB line by 2. Y by 2 na? Y by 2. JB line by 2. This number is also same. JB line by 2 means Y by 2. And this side, sending end side, you have a voltage source. Yes. Yes. And you see, this is a receiving end side. Receiving end side, no load. Receiving end side, I'll say it is no load. IR equals to 0. IR equals 0. Then what is this no load receiving end voltage VR0? What is that no load receiving end voltage VR0? Listen here. Listen. So I'm taking some simple network analysis here. Network analysis. Kindly observe. Kindly observe. Let VR0 is something like mod VR0 at an angle 0 degree. Reference. VR0 is equals to mod VR0 at an angle 0 degree. That's our reference. Take this current as IC1. IC1 current. How is it IC1 current you can experience now? Magnitude, I'll take mod IC1. I don't need to bother about magnitude right now. So I'll say mod IC1. But how is the angle of this? That's the question. How is the angle of this current? Already you said this voltage is at an angle 0 degree. Voltage is at an angle 0 degree. Current will be at an angle plus 90 degree. Current is in leading. Current is in leading. Current is in leading. 90 degree leading. That IC1 90 degree leading current, what you say? That will flow through JX line. That will flow through JX line. Till now, all of you understood this one? Till now, all of you have understood this? So this is a sending end voltage Vs, and this is a receiving end voltage VR0 at no load condition. Vs and VR0. 90 degree leading current. Kavya, you take this voltage into admittance as a current. IC1 current is voltage VR0 into admittance is JB line by 2. Okay. So this is VR0 mod VR0 at angle 0. This JB line by 2, it will be 90 degree. That will be 90 degrees. Okay. Now if you apply KVL from this Vs to VR0, KVL from Vs to VR0, you can write this Vs as Vs is equals to VR0 plus IC1 into JX line. VR0 plus IC1 into JX line. You observe now VR0 is mod VR0 at an angle 0 degree plus IC1 coming like mod IC1 at an angle 90 degrees. Okay. JX line, you write it as X line at an angle of 90 degrees. From this, you can write mod VR0 at an angle of 0 degree plus mod IC1 X line angle will be 90 plus 90, that is 180 degrees. 90 plus 90, that will be 180 degrees. So some magnitude with some angle of 180 means you have to take minus sign. Okay. So you'll get this like mod VR0 at an angle of 0 degree minus magnitude of IC1 into X line. Magnitude of IC1 into X line. So mod VR0 at an angle 0 degree means it is mod VR0. So all are only magnitudes. There is no angle. All are magnitudes, sir. We don't have any angle. So observe now, this is Vs is equal to mod VR0 minus some number. Vs is equals to mod VR0 minus some number. What's the meaning of that? What's the meaning of that? Vsc is less compared to VR0. Vsc is less compared to VR0. Yes or no? Phasor diagrams are not required. Phasor diagrams are not required for this model. We are thinking about GATE exam. Yeah. So definitely this mod Vs value will come less compared to mod VR0. Else you write in reverse. No load receiving end voltage magnitude is greater compared to sending end voltage magnitude. No load receiving end voltage magnitude is greater compared to sending end voltage magnitude. This is what we are naming as Ferranti effect. This is what we are saying in a definition as Ferranti effect. We are saying as Ferranti effect. All of you understood this? I think all of you have understood this. Yeah, fine. Next, let's continue. See how to make this VR0 and Vs values as equal. That's the question now. How to make the sending end voltage and receiving end voltage as equal. See, don't think deeply about it. Sir, charging current IC or why not IC by 2? I have taken IC1. What's the mistake in that? What's the mistake in that? I have taken IC1 according to the voltage and currents. Okay, voltage and numbers. Equations came means these are KVL applications only. Aishwarya, I have not written any new things here. I have written only KVL applications. Yeah, listen now. Look here. See, we have to make this Vs and VR0 values as equal. Vs and VR0 values as equal. What we have to do for that? I'll tell two options now. You have to make this number 0 anyhow. IC1 into Jx line, we should make 0. One option, make IC1 value 0. Means this IC1 current, we should kill down to 0. Next option is making this overall series impedance 0. Making this overall series impedance 0. For that purpose, we have to add series capacitor. But adding series capacitor may create some sort of resonance. Adding series capacitor may create some sort of resonance. You keep this option aside. You try to make this IC1 value less. How to make this IC1 value less? Or how to make that IC1 value 0? How to make that capacitor current as 0? To make that capacitor current value as 0, I will be adding one shunt reactor here. Shunt reactor that will have an admittance value with minus J. Shunt reactor will have an admittance value with minus J. So overall admittance, we will try to make it 0. Overall admittance, shunt admittance, we will try to make it 0 so that this whole branch will not draw any current. So this Jx line will carry 0 current and you will get VR0 and Vs values as equal. Yeah. So what is the simple technique of avoiding the Ferranti effect? What is the simple technique of avoiding the Ferranti effect? Adding shunt reactor at the receiving end side of the transmission line. So I will show in the same model, I'll show here, right? shunt reactor kept at receiving end side. Shunt reactor kept at receiving end side. Receiving end side. Yeah. You see, shunt reactor kept at receiving end side means I am adding that shunt reactor at this place. Like this, we are adding. How is the admittance of the shunt reactor? Minus J symbol. Admittance of shunt reactor is minus J. So it is minus J BR, I will say. BR. So if that BR and B line are same, B line by 2, BR and B line by 2, if these two are equal, overall admittance will be 0. Overall admittance is 0. So this current will drop down to 0. This won't carry any current. So then we can say this VR0 value and Vs value both will be exactly equal. That implies VR0 and Vs values are equal. Okay. So to avoid Ferrand effect, shunt reactor bank has to be kept at receiving end side. Shunt reactor bank shall be kept at receiving end side. Shall be kept at receiving end. Shunt reactor bank shall be kept at the receiving end side. So what is the ground clearance you are saying, Mahivana? Mahivana, what is the ground clearance you are saying here? So Shahil, BR is a susceptance of the reactor. BR is the susceptance of the reactor. Okay. See, actually, the inductor or reactor will have an impedance of Jx something. Inverse of that means it will become minus J, right? Inverse of that means it will be minus J. What happens due to Ferrand effect means we are experiencing a rise in the operating voltage at the receiving end side under no load condition compared to sending end side. We are experiencing a rise in the receiving end voltage with respect to sending end voltage under no load operation. Yeah, so let me continue with this. This bit capacitor plate making high. What is that capacitor plate you are talking? What is that capacitor plate here? Okay. I will show it. I will show it in Imtiaz later. Yeah. So let's continue now. Let's continue. Following Vignesh, I have taken IC1. IC1 I have taken. It's not IC I have taken IC1. Other side you show IC2. What's the mistake in that following case? Huh? So even if I say IC there, is it the meaning to tell you the total charging current is located only one place by keeping capacitor on the other side? Just notations. Those are simply notations. Okay. Practically, we have shunt reactors at various places. Yeah, let's continue now. Let's continue. This ends the medium transmission line analysis a little bit. So this we are discussing only at no load. This all the things we are discussing only at the no load condition. No load condition. And this BR equals to B line by 2 also valid only under no load. BR equals to B line by 2 is valid only under no load. Only under no load to make VR0 equals to Vs. Yeah, so let's continue with the next slide, that is long transmission line analysis. Next heading I'm going to take now, long transmission line analysis. Long transmission line analysis. Else you say Calculating ABCD parameters for the uniformly distributed model. Calculating ABCD for the uniformly distributed model. ABCD for uniformly distributed model. ABCD for uniformly distributed model. Okay. So now I will be showing that approximate model what we have drawn earlier. Approximate model. RLCG circuit parameter model. Yeah. So these are RLCG parameters. So like that we have a number of circuits to be interconnected. Number of sections you can say. Section 1, section 2. And so on. We have n number of sections. N number of sections. And this is your sending end side. I'm showing some source here. And this is the receiving end side. I'm showing some load. Load. And this was source. And this side we have voltage Vs. Current as Is. And this side we have voltage VR. Current here is IR. Next. See here. So from which side we have to start the analysis? From which side we have to start the analysis? Which is a known side and which is unknown side for you? Load side is a known. Load side quantities are known for us and source side quantities are unknown. So we have to start our analysis from receiving end side. Receiving end side by knowing the values of VR and IR. We should update the values of voltage and currents and we should go towards the sending end. We should go towards the sending end. So I will be indicating this point as x equals to 0 point. That's the point of starting the analysis. And this point I will be indicating as x equal to L, where L is a length of transmission line wire. L is a length of transmission line wire. Okay, next thing. First of all, each and every section what we have here is representing 1 kilometer length, we say. So that I will try to take up the per kilometer series impedance of the line and per kilometer shunt admittance of the line. I will be showing in the next slide. Each section represents 1 kilometer length. 1 kilometer length. Okay. So series impedance per kilometer. So per kilometer series impedance. Z is equals to what you can say series impedance R plus J omega L. R plus J omega L. So it will be like R plus J omega L ohm per kilometer. Ohms per kilometer. Next, per kilometer shunt admittance. Shunt admittance. So you can call it small y. It will be like G. Already it is in admittance form. G. What is admittance of capacitor? J omega C. So it will come to be G plus J omega C mho by kilometers. G plus J omega C mho by kilometers. These are per kilometer values. That's why we are going with only. So do these sections? No, no. These are our assumptions, right? These are our assumptions. We are taking only per kilometer series impedance and shunt admittances. Does not have any practical existence for these sections in the practical transmission. Okay, next thing. So if you want to take up the total series impedance and total shunt admittance values, we have to multiply these numbers with the length of line. So total Z, capital Z I'll say, small z into length. And then total shunt admittance will be small y into length. Total shunt admittance will be small y into L. Okay, let's continue. Let's continue now. See, our aim is to express VSIS in terms of VRIL. Our aim is to express VSIS in terms of VRIL. Okay, for that purpose, listen, please. We'll stand at one point here. We'll stand at one point, which I'll say as X point, at a distance of X from the receiving end side. This is at a distance of X from the receiving end side. X from the receiving end side. Kindly listen to me. Voltage and currents at this point X. Voltage and currents at this point X are Vx, Ix. Voltage and currents at that point are Vx, Ix. Okay, next. Listen now. See, we attempt to mention, we attempt to represent Vx and Ix in terms of VRIR first. Vx, Ix, we try to keep in terms of VRIR. Then I will move that X to L, so you get VSIS in terms of VRIR. That will give you ABCD easily. Following all of you. Now, about to that X, I am considering a small length called as delta X. About to that X, I am calling a small length of delta X. Yeah. So this point already we have mentioned as X now, and this point will come to be X plus delta X now. That point will come to be X plus delta X. All of you stop writing. Just I am saying you again. Just try to listen to this. Try to listen what I am saying you. I have taken a point X on the transmission line at which voltage and currents are Vx, Ix. Okay. Just above the X, I have taken a small section of delta X. Very small length. Maybe 0.001 kilometer. 0.001 kilometer. A small section I have taken. Okay. After taking that small section, above that small section, point will be X plus delta X. X plus delta X. Not only that, voltage and currents at this X plus delta X. Voltage and currents at that X plus delta X will be Vx plus delta Vx. One term. Current Ix plus delta Ix. Voltage will be Vx plus delta Vx. Current will be Ix plus delta Ix. We are writing. Yeah, please complete it. If you have understood, please raise your hands. I will be proceeding further. So I will be writing here a small section of delta X was taken at point X. At point X. A small section of delta X was taken at point X on transmission line. On the transmission line. Okay, next. You please tell me what is series impedance of this section? For that section delta X, what is the series impedance? You know, small z is per kilometer impedance, right? small z is per kilometer impedance. So obviously for the delta x section, impedance will be z into delta x. Admittance will be y into delta x. Clear? So z into delta x is a series impedance of that section. Series impedance will be z into delta x, you can say. Shunt admittance will be y into delta x. Y into delta x. Clear? Y into delta x. Next thing. What do you mean by these delta Vx and delta Ix values here? What do you mean by delta Vx? What do you mean by delta Ix? Anybody? Anybody tell me please? What do you mean by delta Vx and what do you mean by delta Ix? Delta Vx is voltage drop. Delta Vx is a voltage drop. Delta Ix is a current drop in the delta X section. Delta Vx is a voltage drop. Delta Ix is a current drop. Okay. What is voltage drop formula? Voltage drop formula is nothing but current flow multiplied with impedance. Current flow multiplied with impedance. What is current flow? Ix. Ix is a current flow multiplied with what is impedance value? Z into delta X. Z into delta X. Okay. So let me write first. In the delta X section, voltage drop delta Vx is equals to current Ix into Z delta X. Current Ix into Z delta X. Clear? Voltage drop. And you see from this one, you can write delta Vx by delta X is nothing but Z into Ix. Delta Vx by delta X is nothing but Z into Ix, you can write. Series impedance per kilometer multiplied with the current Ix. Next, what is current drop in the delta X section? What is that current drop in the delta X section? Delta Ix is a current. Current drop is created by shunt element. Na? Current drop is created by shunt element. Shunt element already we are keeping in the form of admittance. That admittance value what you have multiplied with the voltage applied. Admittance value multiplied with the voltage applied, that will give the current drop. What is voltage applied? Vx. Admittance y into delta x. So you can write this one Vx into y delta x. Vx into y delta x. So from this you can write delta Ix by delta x will be equal to y into Vx. Delta Ix by delta x will be equals to y into Vx, you can say. Y into Vx. I need your response. All of you have understood till this point? All of you have understood? Good. Yeah, next. See, actually, the delta x section length is negligibly small, na? Delta x section length is negligibly small. See, we have one identity in mathematics. That limit delta t tends to 0, delta y by delta t can be written as dy by dt. Like this you can write. We have an identity in mathematics that limit delta t tends to 0, delta y by delta t, we can write it as differential term dy by dt. In the same way, this delta vx by delta x can be written as dvx by dx. This can be written as dix by dx. Clear? Okay. So as delta x tends to 0, as delta x tends to 0, we call it equation 1 and it is equation 2. Equation 1 can be written as, equation number 1 can be written as dvx by dx is equals to z into ix. And dix by dx, equation number 2, can be written as dix by dx equals to y into vx. Dix by dx equals to y into vx. Like that we have it. Yeah. So this is equation number 3, you can say, and this is number 4. Equation 3 and 4. Just look back. What's the aim here? Why we are discussing all these things? What's the aim? Our aim is to find out ABCD parameters of this line. Okay. So to find out the ABCD parameters, we have to express VSIS in terms of VRIR. That's why first we have taken a point X, right? Where I said voltage and currents are Vx and Ix. And we try to express Vx, Ix in terms of VRIR first. Okay. So to get it, we have taken a small length of delta x. In that small length of delta x, we came to know dvx by dx and dix by dx. By solving these two differential equations, we get voltage and currents at any point x on line in terms of VR and IR, and by replacing that x with L, we get the ABC. That's the aim. But you see, integrating this first equation, third one of course, integrating that one, Vx will come like integral Zix with respect to x now. Vx will be like integral of Zix with respect to x. But you see, this Ix is again a function of x, right? Ix is again a function of x, which we don't know. And if you do the same thing for the fourth one, you will get the same problem again. You will get the same problem again. Same problem. So to make this easy, to make this possible, to make the solution easy, I will be going with one more differentiation. Equation 3 I will differentiate again, and then equation 4 also I will differentiate, and I will try to what we call get the resultant equations. Okay. For example, equation 3, if you differentiate again, what you get? D square Vx by dx square. D square Vx by dx square equals to Z into what you get? Dix by dx. Na? The dix by dx you replace with y into vx. Y into vx. So that third equation completely convert in terms of voltage vx. Similarly, fourth one also. Okay. So differentiate equation number 3 with respect to x. So it is d square Vx by dx square is equal to Z into dix by dx. So this will come like Z into y into vx. So if you write this in a standard differential equation notation, you get capital D square minus zy into vx is equal to 0. This is the fifth equation which we can solve easily. Fifth equation which we can solve easily. Okay, done. Next thing. Take up differentiation for equation number 4. Differentiate equation number 4 with respect to x. What you can get now? D square Ix by dx square d square Ix by dx square y into equal to y into dvx by dx. What is the dvx by dx here? What is the dvx by dx? Z into Ix. So if you take up this calculation, you will be getting like d square minus zy into Ix equal to 0. This you call as equation number 6. That you call as equation number 6. d square minus zy into ix equal to 0. That's the equation number 6. Okay. Now, see, what's the solution of equation number 5 and what's the solution of equation number 6? That we have to take. First of all, you observe that both equations looking as same, d square minus zy into vx, d square minus zy into ix, means characteristic equation. Characteristic equation of 5 and 6 is same, that is d square minus zy equals to 0. So I'll write here characteristic equation. Characteristic equation of 5 and 6. D square minus zy is equal to 0. So d square minus zy is equals to 0 means you can say d square equals to zy here. And you can call here d is equals to plus or minus root zy. D is equals to plus or minus root zy. Plus or minus root zy. Okay. Next thing, what it is representing. See, we know small z value some number per line. Small y value also we know some number. We'll substitute that. We'll get some value here for capital D. What is that capital D? What it is saying actually? What that capital D is saying for us? Anybody? What that capital D is saying for us? That capital D is nothing but d by dx, right? That capital D is nothing but d by dx. Means what? Change. D by dx in this is what? Change. Change in what? Change in what? Voltage and currents. Because this is a characteristic equation corresponding to this current and voltage, na? Corresponding to that current and voltage. So it will tell you the changes occurring in voltage and currents with respect to x. Means with respect to movement on the transmission line. See, if the voltage and currents are moving on the transmission line, what are the changes we can experience for that voltage and the currents? That is governed by the term root zy. Root zy. It is going to be called generally propagation constant. It's going to be called as propagation constant. So the next heading, small heading under the same topic we are going to discuss is propagation constant root z into y. Okay, so I'll say here propagation constant. Generally, it is indicated with a letter gamma. Where you can say gamma is equal to root of small z into small y, and you write it represents the changes occurring for voltage and current waves. Current waves moving on the transmission line. It represents changes occurring for the voltage and the current waves moving on the transmission line. Okay, so I'm showing previous page. If anybody is still writing, please complete it. Anybody tell me, think about this one for time being. What are the changes you can experience now? See, if the voltage and currents are moving from one place to other place, what are the changes you can experience? Anybody? Two changes you can get. One, magnitude change. Second one, phase angle. Sinusoidal wave. Magnitude variation, one thing. Next one is a phase angle variation. These two variations are governed by the term root zy. Okay. So I'll say changes means two things we are saying. Magnitude decrement you say sometimes, or magnitude change. Next one is a phase displacement. or phase angle variation. Phase angle variation. Let me continue with the gamma later. Root z by z and y we substitute. We extend that and we'll conclude. So gamma, it will be square root of z into y. R plus j omega m. Y is g plus j omega. So it's a multiplication of two complex numbers. Resultant is a complex number. Multiplication of two complex numbers, it's a complex number. Square root of that complex number will be a complex number which will have some real part and some imaginary part. It will have some real part as well as some imaginary part. So I'm taking only gamma root z by, that's it. Irrespective of the sign what we have, I'm taking only this one. Okay, see, whatever the real part we have now, alpha, this is going to be called as attenuation constant, which represents the magnitude decrement in the wave. Magnitude decrement in the wave with respect to movement on the transmission line. So alpha is called as attenuation constant. Attenuation constant. It represents the magnitude decrement. Magnitude decrement in wave with respect to x. With respect to x. Okay. And beta, it is going to be called as phase constant. It's going to be called as phase constant. Phase constant or quadrature component. Quadrature component. Okay, so it represents the physical displacement of the wave. With respect to x. With respect to x. Physical displacement of the wave with respect to x. Units of these terms, simple. Alpha units. Generally, attenuation will be measured in decibel. Attenuation will be measured in decibels, but here it will be coming in the units of Nepers per kilometer. Alpha will be in the units of Nepers per kilometer. Nepers per kilometer. Beta units will be radians per kilometer. Beta units will be radians by kilometer. These are the units of the alpha and beta. Alpha and beta. Okay, regarding the phase constant, we will repeat it later. Maybe in lossless transmission line discussion, we will repeat it. Okay. Let's continue with this now. So this is the significance of gamma and alpha beta. Let's go back to the derivation what we are making. You got this D. You got this D here. Two roots you have. One is plus gamma root. Next one is minus gamma root. D, we got two roots. One is plus gamma, other one is a minus gamma. Now, what will be the solution of equation 5? And what will be the solution of equation 6? Solution of equation 5, two roots are distinct. Two roots and moreover these two are distinct. It will come some constant into e power gamma x plus some other constant into e power minus gamma x. Similarly, equation 6 also we can see. Solution. Yeah. So let me write now. Let me continue with the original derivation what we are making. Original derivation. Solution of equation number 5 will be. Solution of equation number 5 will be. What is that solution of equation 5? So that is Vx. Vx is equals to some constant C1 into e power gamma x plus some other constant C2 into e power minus gamma x. Okay. And similarly, solution of equation number 6 will be equation number 6 will be Ix current come to be C3 into e power gamma x plus some constant C4 into e power minus gamma x. C3 into e power gamma x plus C4 into e power minus gamma x. These are waves. These are waves means sinusoidal waves. Nepers is a unit for attenuation. Nepers is a unit for attenuation. So I'm showing 84 here. If anybody is still writing, please complete it. 84. Moving means voltage and current waves only. Yeah. So I'm not going to extend this what we call derivation further. I'm not going to extend it. What you have to do exactly is you have to attempt to find these constants C1, C2, C3, C4 by applying boundary conditions. Maybe by applying condition of x equals to 0. X equals 0, we should find out this voltage and currents Vx and Ix. And I will be giving you the final solution here. Final solution for the voltage and currents is Vx and Ix. So I can say at any point x, after calculating constants, calculating the constants, voltage and currents at any point x on the line, voltage and currents at any point x on the transmission line, Vx is equal to, just follow it, just follow this equation what I'm saying, Vx equals to cos h gamma x into cos h gamma x into Vr plus root of z by y sin h gamma x into IR. Current Ix will come like root of y by z sin h gamma x into Vr plus cos h gamma x into IR. So by these equations, we are capable to get the voltage and currents at any point x on the transmission line in terms of receiving and voltage and currents. In terms of receiving and voltage and the currents. Okay. '85. Page number 85. Anybody writing, please complete it. Page number 85. 85. Okay. Right. So we will take a break here, 15 minutes. After break, we will be continuing with placement of x equals to L to get Vs and Is. Okay. 15 minutes break. So I have resumed audio video on screen. So now let's continue with that x equals to L placement in these two equations. So for x equals to L, so I can say Vx you can replace with Vs, Ix you can replace with Is. Okay. So therefore, you get the sending end voltage Vs is equals to cos h gamma x means cos h gamma L into Vr plus root z by y sin h gamma L into IL. Cos h gamma L into Vr plus root z by y sin h gamma L into IR. Root z by y sin h gamma L into IR. Next, current IS. Current IS. You can get root y by z sin h gamma L into VR. Root y by z sin h gamma L into VR plus cos h gamma L into IR. Like this you can get. Root y by z sin h gamma L into VR plus cos h gamma L into IR. So obviously the ABCD parameters from these two equations will be cos h gamma L, root z by y sin h gamma L, root y by z sin h gamma L, and then we have cos h gamma. So these are the ABCD parameters. These are the ABCD parameters. Next thing. Next thing. Listen, please. Listen. See, we have already discussed about a term like characteristic impedance, right? We have already discussed about a term characteristic impedance root of A by C into B by D. Let me recall that term now. Characteristic impedance. Characteristic impedance. ZC. We are going to say this as ZC. From ABCD parameters, you are capable to get this characteristic impedance as root of A by C into B by D. A by C into B by D. Already you know A and D values are equal right now. Cos h gamma L. So you can write this like root of B by C for the line. Square root of B by C for the line. So you can write now square root of parameter B is root Z by Y sin h gamma L. Parameter B is root Z by Y sin h gamma L. And parameter C is root of Y by Z sin h gamma L. So sin h gamma L will be cancelled out and you will get this ZC. You will get that ZC. Yeah. So you can get this ZC like square root of Z by Y. Small z by small y. So this is a characteristic impedance of the transmission line. Characteristic impedance of transmission line. Root of small z by small y. Else, if you want to multiply with the length in the numerator and denominator, you can get it as capital Z by capital Y also, if you want. Capital Z by capital Y. This is characteristic impedance of transmission line. Characteristic impedance of transmission line, root of small z by small y. Yeah. So let's move ahead with this characteristic impedance little bit. See, listen. Is it depending on length of line? Whether this characteristic impedance value depends upon the length of line or not? No. So even though you multiply with the length in the numerator and denominator, it will be cancelled out. Ratio will be remains constant. So I can say ZC is independent on the length of transmission line. ZC, it is independent on transmission line length. length of line. Length of. Actually, in that Z and Y, major parameters will be L and C, right? Major parameters will be L and C. So you know that this L and C values are mainly depending upon the size of the conductors and spacing between the conductors. Size of the conductors and spacing between the conductors. So this characteristic impedance depends upon the dimensions of the system. Dimensions of the system means, as we said just now, radius of the conductors and spacing between the conductors. So ZC mainly depends on radius of conductors and the spacing between conductors. Spacing between conductors. Radius of conductors and spacing between the conductors. Okay. Yeah. So next, this ZC value. Okay, we'll think about the values of ZC and later ZC value. So let's continue with the equation. Let's continue with the equations. See, you have this root of Z by Y. Root of Z by Y. This you replace with characteristic impedance ZC. And this root of Y by Z you can replace with a term like 1 by ZC characteristic impedance. 1 by ZC characteristic impedance. Now you can rewrite these two equations in the matrix form and we'll get ABCD from that, right? So I can say the generalized equations can be rewritten as generalized equations can be written as sending end quantities VSIS, voltage and currents, equal to, so I have ABCD that I'm going to write. And then here you get VRIR, receiving end side quantities. And this is cos H gamma L, parameter A. Parameter B is ZC sin H gamma L. Parameter C, 1 by ZC sin H gamma L. And parameter D is again you get cos H gamma L. Parameter D will be cos H gamma L. Yeah. And you observe now, these are the exact ABCD of any length of transmission line. See, if the length is 1 kilometer, 2 kilometer, 100, 1000, whatever may be the length of the transmission line, these are the ABCD parameters which will be valid, operating at any frequency. Okay, so these are the exact ABCD of transmission line of any length operating at any frequency. These are the exact ABCD of the transmission line operating at any frequency and of any length. Of course, you know here A and D values are equal. So your uniformly distributed model or practical transmission line, it's a symmetrical one. Uniformly distributed model is symmetrical. And AD minus BC number is 1. So that uniformly distributed model is reciprocal one. Uniformly distributed model is reciprocal one. Reciprocal. So I think all of you getting this, what we discussed till now. Regarding characteristic impedance and a term like surge impedance, we'll discuss again. Just for time being, we have taken up that. Okay. So symmetrical only we got Shahil here. Shahil, we got this one as symmetrical. Yeah, so I'm showing the previous slides. So this is 87 here. I am showing 87. Then the next slide, so 88. I'm going to show 88. Sir, but symmetrical we can't say from circuit diagram. You tell me, Akshay, this is the transmission line wire, what we are seeing outside. It's a transmission line wire, what we are seeing outside. Is it symmetrical or not? This is a transmission line wire, what we are seeing outside, some length, certain length. Is it symmetrical or not? No, that's it. That's the thing what we are saying now. So this is a line for which we have calculated the ABCD parameters. This is a line for which we calculated the ABCD parameters, right? So for this line, if there is a series impedance of per kilometer small z, shunt admittance small y per kilometer, ABCD parameters of that line will be in this manner. Okay. And for this line, you know already propagation constant gamma root zy and characteristic impedance of this line is root of small z by small. Root of small z by small. Yeah. Yeah, that is a model for your understanding only, Akshay. That's a model for your understanding only. But this is the exact one, right? This is the exact one. If you want to show here VR, IR, and you show some point X here, delta X, no issue with that. Yeah. Why did you tell that ZC mainly depends on who said only R and L? I said C and G also. Denominator is Y, right? Denominator is Y. Depends upon definitely C and G also. L and C I said mainly. L and C. Okay. Yeah. See, actually, calculating ABCD by using these numbers, cos h gamma L, sin h gamma L, it is a bit laborious process. Why it is so means we have hyperbolic cosine. Hyperbolic cosine. Gamma L is a complex number again. Because gamma is a complex number now. So gamma L is also a complex number. So hyperbolic cosine of complex number. Hyperbolic cosine of complex number. Calculating this number is a bit laborious. So anyhow, in the present days, we have MATLAB and sophisticated mathematical operations. Just by one click, we are going to get that answer. That's okay. But in olden days, the people are feeling more difficulty in calculating these hyperbolic cosine and sine of complex numbers. At that time, they have gone for some approximations for these things, and they have derived the approximate ABCD parameters of the transmission line. Okay, so those approximate ABCD parameters we are going to discuss. So I'll show in the next slide. The next heading you can say approximate ABCD parameters of long transmission line. Approximate ABCD parameters of the long transmission line. Okay. Yeah. So for this approximation, simply we are going to expand cos h gamma L, sin h gamma L, and we are going to neglect the higher order terms, and then we go for the approximate ABC. The first one, cos h gamma L. Cos h gamma L expansion. Say this. Cos h gamma L expansion by using Taylor series, or you can say Maclaurin series. You can say like this: 1 plus gamma L whole square by 2 factorial plus gamma L power 4 by 4 factorial plus and so on. Like this you can do. Whereas if you think about that sin h gamma L expansion, you will get this like gamma L plus gamma L whole cube by 3 factorial plus gamma L power 5 by 5 factorial plus and so on. Like this, you can get the sin h gamma L expansion. See, we are going to neglect the higher order terms in that. Neglect the higher order terms. Listen please, listen please. Neglecting higher order terms means I will be considering only first two terms. That's it. Consider only first two terms. Remaining all terms we are going to remove from our study. When it is possible to remove these higher order terms means these are higher order terms. Higher order terms can be neglected. Can be neglected for a condition of gamma L magnitude less than 1. For a condition of gamma L magnitude less than 1, we can neglect these higher order terms. Okay, listen. Listen, all of you, stop writing. Stop writing. Stop writing. Just listen. Just listen. See, gamma L less than 1 is the thing what we are asking. Gamma, it is root of z by y. It may be a constant number. Let me assume. Constant number. Then who will decide? Who will decide whether this gamma L is less than 1 or equal to 1 or more than 1? That is definitely length of line. Length of line. See, if the length of the line is very, very high, length of the line is very, very high, then definitely gamma L value may become more than 1. At that time, this approximation may not be valid. Neglecting these higher order terms may not be valid. The length of the line is very, very large. Then up to what length? Up to what length of line this is valid? Means generally for a length less than 500 kilometers. Okay. So these approximate ABCD what we are discussing now, these are valid for a length of line less than 500 kilometers. Less than 500 kilometers. Clear? 500 kilometers. So now, what are the parameters A and D? Exactly speaking, cos h gamma L, cos h gamma L. In place of that cos h gamma L, you can keep that as 1 plus gamma L whole square by 2 factorial. 2 factorial. Okay. So now I can write here, parameters A and B are equal to cos h gamma L. So which will be approximately 1 plus gamma L whole square by 2 factorial means it is 2. What is that gamma L whole square? What is that gamma L whole square? Let's take like this. Gamma L whole square equals to gamma square L square, you can say. Gamma L whole square equals to gamma square L square. What is that gamma square? Root zy whole square L square. Okay. Now you can say it is zy L square. Means it is z into L, y into L. Z into L, y into L. What is it z into L? Capital Z. Y into L, capital Y. Capital Y. Okay. So now you can say parameters A and D approximately equal to 1 plus zy by 2. Approximately that A and D you can write it as 1 plus zy by 2. Approximate values of A and D will be 1 plus zy by 2. Next thing. Parameter B. Parameter B. We know it is ZC sin h gamma L exact. We try to replace it. Parameter B exact will be ZC sin h gamma L. You keep ZC as it is. And I will be keeping that sin h gamma L now. Approximately sin h gamma L, you can write gamma L plus gamma L whole cube by 3 factorial. Gamma L plus gamma L whole cube by 3 factorial. 3 factorial means it is 6. 6. Okay, let me take up this ZC root of Z by Y. You can take gamma L common here. Gamma L common. So you can get ZC gamma L 1 plus gamma L whole square by 6. 1 plus gamma L whole square by 6. And if you take up this calculation, and proceed further. Finally, what you can get is capital Z into 1 plus zy by 6. Capital Z into 1 plus zy by 6. This is the parameter B. Parameter B, capital Z into 1 plus zy by 6 you can get. Yeah. So you have to do it. You have to do it. You have to expand, substitute gamma, and take up that. Yeah. So next, similarly, if you go for the parameter C calculation, also parameter C calculation also you can see here. C, we know it is 1 by ZC sin H gamma L. 1 by ZC sin H gamma L. And you can write this approximately 1 by ZC sin H gamma L, you can keep as it is gamma L plus gamma L whole cube by 3 factorial in the sense 6. And proceed with this. Finally, you can get the C approximately. C, we are going to get approximately capital Y into 1 plus zy by 6. Capital Y into 1 plus zy by 6. This is that parameter C, we can say. That's the parameter C. Parameter C. So these are the approximate ABCD of long transmission line. Approximate ABCD of long transmission line. Next. All of you kindly check back to the calculations we have done today in the medium line. Yeah, please complete it. I will wait for 10 seconds. Once after completion, please raise your hands. Okay, good, good. Yeah, just listen here. We can't put sin H gamma L equals to B here. No, we didn't kept it. We have taken ZC sin H gamma L. Yeah, listen now. See, actually, in the previous cases, we calculated a number 1 plus zy for some values of z and y. And we calculated 1 plus zy by 2 also, right? So what that 1 plus zy you got? You don't need to write this, just check. 1 plus zy magnitude you got like 0.98. And you know 1 plus zy by 2 magnitude, you got this something like 0.99. 1 plus zy by 2, you got that like 0.99. Please kindly cross-check the question. What you are asking me, Sweta. Please kindly cross-check your question. Listen, please. 1 plus z by magnitude 0.98. 1 plus z by 2 magnitude 0.99. For example, you take 1 plus z by 4. How is that magnitude? Will be very close to 1. 1 plus z by 6. It will be again very close to 1, you can see. So in that perspective, we can approximately say 1 plus z by 6 is close to 1. 1 plus z by 6 is close to 1. By that way, this parameter B is representing series impedance, C is representing the shunt admittance of the line. B representing series impedance of line, C representing the shunt admittance of the transmission. Following all of you, right? So if you compare these ABCD parameters with the nominal T and nominal pi models, for example, nominal T you take. Nominal T. What are the ABCD of nominal T? 1 plus zy by 2, z into 1 plus zy by 4, y, 1 plus zy by 2. So 1 plus zy by 2, 1 plus zy by 2. Now, in case of approximate ABCD also, you are getting same 1 plus zy by 2. Parameter B for nominal T. Z into 1 plus zy by 4. Now what you are getting? Z into 1 plus zy by 6. Parameter C for nominal T, y. And here also you are getting close to y. See, means nominal T model parameters and long line ABCD parameters, both numbers will come close. Nominal pi. A and D, same, 1 plus ZY by 2. Parameter B in the nominal pi, Z, here also close to Z. Parameter C in the nominal pi, Y into 1 plus ZY by 4. Here you get Y into 1 plus ZY by 6, close. This nominal pi model also have almost same ABCD parameters. As of long transmission line model. So what's the conclusion we have to make now? Tell me please. What's the conclusion we have to make now? For limited length of line, for limited lengths of transmission lines, ABCD parameters are nominal T model, nominal pi model, exact transmission line model will be almost equal. So that we can use that nominal T and nominal pi as a replacement for the long transmission line for medium lengths of the transmission lines to reduce the calculations. So I don't know whether you have understood these comments or not. All of you understood this? The ABCD parameters of nominal T, nominal pi, and exact transmission line models is almost same. For limited lengths of lines. For limited lengths of transmission lines. So these three models in bracket, nominal T, nominal pi, comma exact, will give almost same analysis results. Yeah, okay, Vishnu, I understood your question, but you see, if the length of the line is crossing certain level, it is better to go for long line only for accuracy. But I will say nominal T and nominal pi even up to 500 kilometers length will give a good result, may not be accurate. Yeah. Will exact model can be used for short? Yes, you can use it. We can use the exact model even for the short transmission lines. Can we use nominal T and nominal pi? Yes, that's what we discussed long back, Shruti. Okay, let me continue now. See, actually, the original way of discussing this transmission lines will be like this. Strictly speaking, first we should do the analysis of the long line, which is exact one. Distributed model analysis we have to discuss first. For that, we find the ABCD parameters. Okay. So after that, we have to go for medium line as an approximation of long line. Medium line we should go as an approximation of long line. Now, could you please tell me, in the medium transmission line, we said 4 models, na? 4 models. In the 4 models, which models we should use? For analysis? Only nominal T and nominal pi we have to use. We should use nominal T and nominal pi, because only these 2 models are giving almost same results as a long transmission line. But even if the length of the line is very, very less, shunt element can be neglected and we can represent that as a single series impedance. That's the way of doing the approximation exactly. Yeah, we have to remember. We have to remember these approximate as well as exact parameters. Both. Yeah, fine. So I think so. This is about the ABCD parameters of different lines we have seen, short, medium, and long. Now we are moving on to some sort of conclusions. Some conclusions on the ABCD parameters of the transmission lines, what we have discussed till now. Okay. So I am taking up in the next slide. That's the next heading. Conclusions. Conclusions on ABCD parameters of transmission lines. Conclusions on ABCD parameters of transmission lines. Yeah. First one. Conclusions in the sense how we are going to represent these things that we are going to discuss. First of all, ABCD parameters, whether these are per phase numbers or line to line numbers. Actually, there is no meaning for line to line. There is no meaning for line to line. These are per phase calculations only. And whether these are real numbers or complex numbers. Complex numbers, because we are dealing with inductive reactances and capacitive susceptances. So these are complex numbers, you can say. So ABCD are calculated per phase, and moreover, these are complex numbers. Complex numbers. These are calculated per phase, and moreover, these are complex numbers. Okay, next thing. So as these are complex numbers, I am going to represent these ABCD in the polar form. Polar form is the magnitude associated angle. So before writing that ABCD, I will write the generalized equations here. Vs equal to AVR plus VIR. Okay. Next, sending end current Is equal to C into VR plus D into IR. Vs equal to AVR plus VIR. Is equals to CVR plus DIR, we can see. One thing, listen. Whatever the voltage and currents we have in the two equations, these are phase values, per phase values, voltage and currents. So it's a Vs phase, VR phase, IR phase. Similarly, Is phase, VR phase, IR phase. Not only that, these are simply resultant KVL KCLs, right? Generalized KVL KCLs. So not only that Vs phase, we should say this one Vs phase bar. Magnitude as well as angle, both we have to substitute. Okay, for clear identification, I'm keeping it is Vs phase bar equals to AVR phase bar plus VIR phase bar. Is phase bar equals to CVR phase bar plus D into IR phase bar. Like that, we have to remember and we have to write it all the time while we are doing the mathematical calculations. Okay. Now, let me take up that ABCD in the complex form. Maybe in the polar form, I will take polar form. First, parameter A, I will be writing as mod A at an angle alpha, some magnitude and associated angle. B, mod B at an angle beta. C, mod C at an angle gamma. D, mod D at an angle delta. A equals to mod A at an angle alpha, B equals to mod B at an angle beta, C equals to mod C at an angle gamma, D equals to mod D at an angle delta. Like this you can write ABC. Like that you can write ABC. Next thing. See, already you know that parameter B is representing series impedance. I'll write it in the next slide. B representing series impedance means you can write B approximately equal to Z represents series impedance. Series impedance. So B is approximately Z. Z means what? R plus JX. R plus JX means it will have some magnitude mod Z associated angle theta. It will have some magnitude mod Z and then we have some associated angle as theta. Next B, we will write it as mod B at an angle beta. B we are going to take it as mod B at an angle beta. And you observe now, mod B and mod Z values are equal. Beta equals to theta. See this. Mod B approximately mod Z, which is square root of R square plus X square. Beta is approximately theta, which is nothing but tan inverse of X by R ratio. Tan inverse of X by R ratio. Mod B approximately mod Z, which is root of R square plus X square. Beta is approximately equals to theta, which is nothing but tan inverse of X by R ratio. Next thing, listen please. Listen. See, how is this angle theta we can experience? Maximum angle, how much you can say? Theta. Maximum angle, how much you can say for theta? 90 degree. If that X by R is very, very large, X by R ratio is very, very large, you can experience that number 90 degree. How much is minimum angle? Minimum angle may not be zero. Minimum angle may not be zero, particularly with respect to transmission line. Particularly with respect to practical transmission lines, this theta will come in the range of 50 degrees to 90 degrees. The theta will be in the range of 50 degrees to 90 degrees. That's the same range we can experience for beta also. Beta also comes in the same range of 50 to 90 degree, practically speaking. So I can say here, beta will be in the range of 50 degrees to 90 degrees. Beta will be in the range of 50 degrees to 90 degrees. Okay, so I think all of you getting this. Next. Simple question. X by R ratio, is it depends upon length of line or not? X by R ratio, is it going to depend on length of transmission line or not? Tell me please. It is independent on the length of line. Independent on length of transmission line. Right? It is independent on the length of transmission line because X depends on length proportional to length, R proportional to length. If length is doubled, X value doubled, resistance doubled, X by R ratio constant. Say for 5 kilometer length, X by R ratio 2. X by R ratio is 2. For 100 kilometers length of same, X by R ratio only remains same as 2 only. That's the meaning. Okay, fine. Next. See, this is one question generally we used to get in examination for practical transmission lines. For practical transmission lines. How is the X by R ratio of a 400 kV line compared to X by R ratio of a 220 kV line? Simple, very simple. For practical transmission lines, how will be the X by R ratio of the 400 kV line compared to X by R ratio of the 220 kV line? Is it more or less? That's the question. Is it more or less? I'll show in the next slide. Listen, all of you, don't confuse. Don't confuse here. Kindly listen. This is one 400 kV line. 400 kV line. It is going to be divided into a 220 kV line or converted into 220 kV line by using a transformer. I am showing that transformer here. Transformer, primary 400 kV, secondary 220 kV. Primary 400 kV, secondary 220 kV. My question is, from this 220 kV bus, will only one line will run out or number of lines will come? From the 220 kV bus, do you get only one line or number of lines will come? Definitely number of lines, right? Not one. If it is only one, why you are converting it? Why you are converting it? Yes or no? Right. So we get number of lines coming out. Maybe like this. Let's say 3 lines I am taking. 3 lines. See, listen now. Listen carefully what I am saying. This 400 kV line is having a power rating of 450 MVA. 400 kV line is having a power rating of 450 MVA. Transformer. And it is converted into 3 lines out. 3 lines. Then each line power rating might be 150 MVA. First line 150, second line 150, third line is also 150 MVA. Getting this? 150 MVA. Each line will have a rating of 150 MVA. See, obviously, if you talk about a practical transmission line, 220 kV line power rating will be definitely low compared to 400 kV line rating. 220 kV line power rating will be definitely less compared to the 400 kV line power rating. Not only that, current rating of the 220 kV line is also less compared to 400 kV line. Current rating of the 220 kV line is also less compared to 400 kV line. Now, if you take up the area of cross-section comparison, this is a area A1, this is a area A2. Which area looks to be bigger? Which area looks to be bigger? Tell me, is it A1 or A2? Definitely A1 because of high power rating, else you can say high current rating. Because of that, A1 will be definitely greater compared to A2. A1 will be definitely greater compared to A2. Now the thing is, if A1 area is more, how is the resistance of this wire compared to the 220 kV line? R1 compared to R2 will be less per kilometer. How is the R1 compared to R2? Less? Yes or no? Tell me please. Less. Good. Next. Yeah, next. See, if the resistance of 400 kV line is low, definitely X/R ratio of the 400 kV line looks to be greater compared to 220 kV line. Definitely. X/R ratio of the 400 kV line will be greater compared to 220 kV line for unequal power ratings. Power ratings are unequal here. In bracket for unequal power ratings. Unequal power ratings, where practically speaking, 220 kV line power rating is less compared to 400 kV power rating. All of you understood this. Next, you see, after some distance, this 220 kV line might be connected to one more transformer. It may be 220 kV by 132 kV, 130 kV, and number of 130 kV lines are going out. Then again, power is getting divided now. So it may be 50 MVA, 50 MVA, 50 MVA. 50 MVA, 50 MVA, 50 MVA. Then obviously, if you check this conductor size, that will be definitely low compared to 220 kV line size. 130 kV line size will be definitely less compared to 220 kV line size. Then obviously this conductor resistance will be even more per kilometer compared to 220 kV. Now, if you take up that X/R ratio comparison, here, X/R ratio of the 400 kV line will be greater because resistance is low. X/R ratio of 220 kV line greater compared to X wire ratio of 132 kV line, greater compared to X wire ratio of 33 kV line, and so on. Practically, this statement is valid only for practical system of unequal power ratings. Can anybody tell me why we are neglecting X here? Can anybody tell me why we are neglecting X? Why we are not discussing about X? Why you are talking about only resistance? Is on, yeah, because already we said the starting class that inductance value for any transmission line comes only in the same range of 1 to 1.2 millihenry by kilometer. Generally, inductance value will be more or less constant. How unequal power rating I have explained just now. Balavignesh explained. One 450 MVA line divided into 3 lines of different ratings. Yeah. So inductance value will be more or less same. Inductance value will be more or less same. So X value per kilometer will be more or less same. That's why we are not thinking about X. We are thinking about only resistance of the conductors. Yeah. Next, let's continue. Previous slide. So regarding beta and theta X wire ratio, all things we have discussed up to this point. Let me talk about mod B. Mod Z, root of R square plus X square. But you see this value, root of R square plus X square value, mainly depends upon the length of line. The length of the line is increasing. Resistance, reactance will increase. Mod Z value will definitely increase. So I can say mod B, I'm not going to give any range for mod B. I'm not going to give any range for the mod B here. I'll say simply mod B mainly depends on length of line. Mainly depends on length of line. Length of mod B value mainly depends upon the length of the transmission line. X value is almost same. X value is almost same because inductance value is almost same for any transmission line we have mentioned per kilometer. Yeah, next let's talk about the parameter C here. Parameter C, it is representing shunt admittance of line. Represents the shunt admittance of line. Shunt admittance of line. And you can call here parameter C, we are going to take C. Approximately shunt admittance. C is approximately shunt admittance. What do you mean by shunt admittance? J omega into capacitance. J omega into capacitance. Right? Shunt admittance is J omega into capacitance approximately. This you can call modulus of Y at an angle of 90 degrees. Modulus of Y at an angle of 90 degrees. So C is approximately Y in the sense mod C at an angle gamma approximately equals to mod Y at an angle 90. Where you can observe that mod C and mod Y both are almost same. And gamma is close to 90 degrees. Gamma value close to 90 degrees. That's a comment you should make. Gamma close to 90 degree. And this mod C value is mod Y, na? Mod Y. Because that mod Y mainly depends on length of line. If length is increasing, mod Y also increases, mod C also increases. So I can say mod C value mainly depends upon the physical length of the transmission line. So I am not interested to give any range for that mod C here. Okay. So mod C mainly depends on length of transmission line. Length of transmission line. Mod C value mainly depends upon the length of transmission line. Done. Next, parameter A and D. These two will say. These two. Parameter A and parameter D. How is the modulus of A value? parameter A. How is the modulus of A value? Will it come more than one, practically speaking? Mod A value, will it come more than one practically? No. It won't come more than one. It will be always less than one. You can say less than one. Not only less than one, the value will be very close to one again. Maybe you get like 0.95, 0.96. Like that, you are going to get the modulus of A value. So, mod A less than or equals to 1. Not only that, very close to unity, practically speaking. Practically speaking, it's very, very close to unity. How is alpha? How is alpha? It's a very, very low angle. Alpha is very, very low angle. It will be in the range of 0 to 10 degrees. Very, very low angle, positive. We have done some calculation of A, na? We have done some calculation of A. From that only I am saying, I got some angle like 0.4 degree. That in the range of 0 to 10, very, very less angle, positive, positive. Okay. Next, D, parameter D. Parameter D. This conclusion of D same as A will be same as A. So mod D less than or equals to 1. You can call it's very close to unity. Again, delta angle will be in the range of 0 to 10 degrees. Delta angle will be in the range of 0 to 10 degrees. These are some conclusions about these ABCD parameters with respect to their angles as well as their magnitudes. Both mod B and mod C. I have written both, right, Vikrant? Vikrant, I have written both. Both I have written here. Mod B and mod C. Yeah, okay. Now, I want to know what will happen to these ABCDs. What will happen to these ABCDs with respect to increment in the length of line? If length of line is getting increased, what will happen to these numbers? That we should know. Let's see. Variations in the ABCD with respect to length of line. Variations in ABCD with respect to length of transmission. I will take the same example problem which we have taken earlier, numerical problem we have taken. No, that problem I am going to recall. Okay, go through it. Case 1. Length of transmission line 150 kilometers. Series impedance of line 20 plus J50 ohms. Shunt admittance of line J4 into 10 power minus 4 mho. Length of line 150. Small z, sir, capital Z, 20 plus J, 50 ohms. Why? J4 into 10 power minus 4 mho. See, simply in the exam, they have given a line with some series impedance, shunt admittance. Asked you to calculate parameter A. Didn't mention what model it is. It didn't mention what model it is. Simply asking, calculate parameter A. Okay. What's the formula? What's the formula for A you use? 1 plus zy by 2. 1 plus zy by 2. Yes or no? Yeah. 1 plus zy by 2. That you can use safely, no issue. So you can say 1 plus zy by 2. So I can keep these numbers. Already we have calculated this number, I think. That you repeat here. Already we have taken these numbers in the previous calculations. Particularly in medium line calculations, we have taken up these numbers that I am repeating. Anybody tell me what's this magnitude and angle? Magnitude and angle. I think 0.99 is a magnitude and the angle is 0.2 degree. Is it? Medium line. Tell me how much is the angle? 0.234. 0.234 degrees. No units, no units. Now make the length of the line double. Modify the value of Z and Y and calculate the parameter A. Case 2. Case 2. Length of the line I am going to make double. Means it is 2 into 150. It will come 300. It will come 300 kilometers. 2 into 150, in the sense you get this value like 300 kilometers. What will happen to capital Z? Definitely double. Capital Z value double. So it will come 40 plus J 100. 40 plus J 100. Capital Y also double. J4 into 10 power minus 4 into 2. So it will come J8 into 10 power minus 4 more. So after getting that capital Z and capital Y, for double the length of line, calculate parameter A, 1 plus Z by 2. Parameter A will be like 1 plus Z. Approximately same formula, na? Approximately, even though the length of the line is what we call 300 kilometers, but still A will be approximately same formula by using approximate ABCD of long line. So if you do that, A is equal to 1 plus Z Y by 2. 1 plus ZY by 2. So anybody getting this? Magnitude and angle 0.96 or 95. Cross check that. Is it you are getting? Some people are saying this answer. 0.96, 0.9495 degrees. Okay, approximately. So no units, no units. That's A. See, if the length of the line is getting increased from 150 to 300, if the length of the line was increased from 150 to 300, what happens to mod A number? Earlier it is 0.99. Now this number is coming 0.96. So mod A value was decreasing with respect to increment in the length. Alpha, angle alpha. Earlier 0.234. Now it is 0.95. Alpha value increasing. Clear? So length of line increases. Length of the line increases. Mod A, it is decreasing. Alpha increasing. Mod A value was decreasing. Alpha value was increasing. ZY by 2 only. Written 4 here. By 2 only I have taken. What's there? What's doubt you have, Pratik? Yeah. Next thing. ZY by 2 plus 1. Okay, what is there in that? What is there in that, Pratik? What's your doubt? What's your doubt, Pratik? Y plus 1. We have derived earlier, no? Parameter A. Yeah, next. Parameter B. Think about this one. Parameter B magnitude and beta. What will happen? Parameter B magnitude and then beta. What will happen? See, if length of line is increasing. Length of line is increasing. Listen please. If length of line is increasing, series impedance magnitude is increasing, right? Series impedance magnitude is increasing. So obviously parameter B magnitude increases. Parameter B magnitude and mod Z is same. So mod B increases. What happens to beta? What happens to beta? It is almost constant because it depends upon X bar ratio of line. As X bar ratio of the line is almost constant with respect to length. So beta will be constant. Beta is almost constant. Almost constant. Next, mod C. Parameter C, you tell me please. Parameter C. See, parameter C. If length of line is increasing, shunt admittance is increasing. So definitely mod C value will be increasing, but associated angle gamma, it is almost constant. Gamma is almost constant. Almost constant. And parameter D, if you talk, parameter D, mod D, same as A, decreases, delta increases. Same as alpha. Alpha and delta, same change, and A and D also have same change. Yeah. So these are the changes expected in the ABCD with respect to length of line. What will happen to Farrant effect? Anybody? What will happen to Farrant effect? Will increase because A is decreasing now. Because of decrement in the A, I can say Farrant effect in the transmission line increases. Farrant effect in the transmission line increases. Farrant effect in the transmission line increases. Right. Now we'll take some problems in this one. Yes, I have shown previous slide. Satish, already we said B is nothing but series impedance, right? Beta is independent on the length. Beta is nothing but theta. Theta is tan inverse of x by r ratio. Beta is nothing but theta. Theta is tan inverse of x by r ratio. X by r ratio is independent on the length of line. So theta is independent on the length. Beta is also independent on the length. Mod B value depends upon the length of line. I didn't say gamma is constant anywhere. Which gamma? Okay, that angle. Okay. This angle is constant with respect to length because it will be close to 90 degree all the time. Gamma will be close to 90 degree all the time. So even though the length of the line is increasing, this magnitude may increase. The angle will be almost same. Angle will be almost same. Yeah. So let's take some problems now. See this? First question. Use calculator. Just check the procedure how you are solving. Check the procedure how we are going to solve this problem. That's the important one to know. Since the generalized circuit constants of a three-phase 220 kV rated voltage medium length transmission line are A equal to D 0.936 at an angle 0.98 degree, B 142 at an angle 76.4, C minus 5.18 plus J914 into 10 power minus 6. If the load at the receiving end side is 50 megawatt, load at the receiving end side is 50 megawatt at 220 kV with power factor of 0.9 lag. Okay. Then the magnitude of line to line receiving end voltage, when the load is suddenly thrown off is how much? Simply, he said the load voltage. He said the load voltage, right? Load voltage. And what he's asking now, after removing that load, how much is the voltage at the receiving end side of the line? That's the question. Simple. Let's take here. See, if any problem, if they give by using ABCD parameters and all, it is always suggestible. It's always suggestible to show that in a two-port network model. Show that in a two-port network model, then you think about what he is asking in the calculations. Yeah, let's say in the two-port network model, if you show, this is our transmission line, ABCD. Okay, so this is our source location. I will show. So it's plus minus Vs you have, and it's a current Is. Receiving end side, I am keeping some load. Receiving end side, we are keeping some load, and this is voltage VR. Current here is IR. But these are only phase values we have to substitute. We have to substitute only phase values. I'll keep Vs phase bar, Is phase bar, IR phase bar, VR phase bar. These are only phase values. We have to keep. Okay, next thing. Listen, next thing. Load at the receiving end side is at 50 megawatt. 50 megawatt is obviously three-phase power. Okay, 220 kV line to line receiving end voltage. P load 50 megawatt three-phase. Line to line receiving end voltage 220 kilo. Line to line receiving end voltage is 220 kilo. Next, load power factor he mentioned. Load power factor he said that is 0.9 lag. 0.9 lagging. Okay. See, we have to calculate this receiving end voltage by disconnecting the load. Listen all of you. Receiving end voltage by disconnecting the load is nothing but the calculation of no load voltage only. That's nothing but the calculation of the no load voltage of transmission line. What do you mean by no load voltage of line? VR0, which is nothing but Vs by A. No load voltage of the line is our requirement. VR0, which is nothing but Vs by A. What is parameter A? Already we know in the data that will substitute. What is Vs? What is Vs? We don't know. To calculate that Vs only, they provided this load data along with the receiving end side quantities. So what is Vs phase? A VR phase bar plus B into IR phase bar. Vs phase bar equals to A into VR phase bar plus B into IR phase bar. Okay. So what is VR? Line to line is at 220. You take VR phase, how much first? Then you take that as reference. Calculate IR phase. Keep angle for that. Then you go for the Vs phase calculation. Clear? Yeah. You see from this, magnitude of the receiving end phase voltage 220 kilovolts by root 3. 220 kilovolts by root 3. This number will be 127.017. 127.017 kilovolts. That's a VR phase. Now, IR phase, how to calculate? IR phase. We know that load power demand three-phase value 3 into VR phase magnitude into IR phase magnitude multiplied with the power factor of load. 3 into VR phase magnitude, IR phase magnitude multiplied with the power factor of load. Yes or no? Now from this you can get the current. IR phase magnitude equals to P load 50 mega by 3 into VR phase, just now we have taken up. this number, power factor is 0.9. Power factor is 0.9. Okay, calculate this one. How much? 50 mega by so this is 145.8, you can say, amperes. 145.8 amperes. Getting? Okay, fine, fine. Is it required to keep any angle for this? Yes, because already he said load power factor cos phi L 0.9 lagging. Means that the cosine of angle between VR phase and IR phase. Cosine of angle between VR phase and IR phase. Let us take that VR phase as reference. Let VR phase bar taken as reference. So that you can write VR phase bar value is equal to 127.017 at an angle 0 degree in kilovolts. What will happen to IR phase bar? Magnitude is 145.8. Magnitude is 145.8. Now let's look at this power factor angle. Power factor angle is 25.84 degree. Cos inverse of 0.9. 25.84 degree. Means what is it understood is current IR phase is in lagging with respect to voltage. Lagging with respect to voltage by 25.84 degrees. So you can say here 0 degree minus 25.84. 0 degree minus 25.84. So this will come like 145.8 angle will be minus 25.84 degrees. Yeah. So after getting this voltage and currents, now you can go with the sending end voltage equation. Sending end voltage equation. Vs phase bar is equal to A into VR phase bar plus B into IR phase bar. Right here, if you want, IR phase bar lags VR phase bar by an angle phi L, which is 25.84 degree. That's why you get the negative symbol here. That's why you get the negative symbol. Okay, done. Let me substitute these values of ABCD, A and B. A 0.936 at an angle 0.98 degree. 0.98 degrees. VR phase bar is 127.017 kilo. Of course, at an angle of 0 degree plus parameter B 142 at an angle 76.4. 142 at an angle 76.4 degrees. And then IR phase bar 145.8 at an angle minus 25.84 degrees. Take this magnitude and angle calculation. Just go through the procedure. Go through the procedure. Yeah. This magnitude may come around 133.247. 133.247 magnitude, and angle will be 7.77 degrees in kilovolts. In kilovolts, you'll get that. Check that. Check that carefully. Check that value carefully. Don't commit a mistake. In the exam, they may give some flexible numbers. In the exam, they may give some flexible numbers. No issue with that. Just go through the procedure of your solving. Okay, so let's look back to the question what he is asking exactly and why we are doing all these things. See, according to the question, what he is asking is, what is that line-to-line receiving end voltage when the load is disconnected? Means we need to find out the no load voltage of the transmission line. That's VR0, which is Vs by A. Already A I know, so we have to get the value of Vs. That's why we are doing all these calculations. Now, if the load is getting disconnected, I'll show in the next step. Next step, I'll show. If load got disconnected, disconnected. I'm repeating this circuit, but I will be removing this load. So this will carry zero current now, load. IR phase bar also falls down to zero. And this VR phase bar, I will be replacing with a term like VR0 phase bar. VR0 phase bar. And what is that VR0 phase bar? What is that VR0 phase bar, you can say? That is nothing but Vs phase bar by A. VR0 phase bar is nothing but Vs phase bar by A. What is Vs phase bar we have done? That is 133.247 angle 7.77 degrees by parameter A. Parameter A is 0.936 at an angle 0.98 degree. At an angle 0.98 degree. You take up this magnitude and angle. So 133.247 by 0.936. So I need only magnitude. So I will write only magnitude in the next step. I don't need to bother about the angle because he is asking us to get only magnitude of voltage. 142.357. 358 kilovolts. That is VR0 phase magnitude. VR0 phase magnitude. But he is asking us to get line-to-line value, right? Line-to-line value means this we should multiply with √3. This we have to multiply with √3. Okay. So no load line-to-line voltage magnitude is √3 into 142.358 kilo. So √3 into 142.358 kilo. So it is 246.57. 246.57 kilovolts. Yeah. So this is one of the model in the exam. To calculate no load receiving end voltage or to calculate the receiving end voltage when the load is disconnected. Yeah, you are correct, Imtiaz. Correct. Yeah, let's take one more problem in this area. Just go through it. It's a previous GATE examination question. Previous GATE examination question. Simple one only. Go through it quickly. Go through it and try to answer. Yes. The ABCD constants of a 220 kV transmission line. ABCD constants of a 220 kV line are A equals to D 0.94 at an angle 1 degree. B equals to 130 at an angle 73 degrees. C 0.001 at an angle of 90 degrees. If the sending end voltage of the line for a given load delivered at nominal voltage is 240 kV, the percentage voltage regulation of transmission line is dash. Yeah. Tell me, first of all, according to the data what they have mentioned, parameters ABCD are there, that's okay. First, you read this statement what they have given. If the sending end voltage of the transmission line for a given load delivered at nominal voltage is 240 kV, means what is the 240 kV given in the data? What is the 240 kV given in the data? Tell me please. Is it sending end voltage or load voltage? Is it sending end voltage or load voltage? Yeah. It will be sending end voltage. Load is going to be delivered at the nominal voltage. That's the meaning. Load is delivered at nominal voltage. At that time, the sending end voltage is 240 kV. So I can say sending end voltage is 240 kV. Of course, you know it is line to line voltage magnitude. Line to line voltage magnitude. Okay, next. Load delivered at nominal voltage. Load delivered at nominal voltage means VR value magnitude equals to 220 kV. That will be again of line to line. That will be again of line to line. Now he is asking us to calculate the voltage regulation, which is modulus of Vs by A minus mod Vr by mod V. Which values we have to substitute in these equations? In this voltage regulation equation, which value we have to substitute? You can do like that, Pratyusha, if you want. Yeah. Tell me, which one? Line to line or phase? Anything you can use will give the same answer. Anything we can use that will give the same answer. So let's say line to line substitution directly. So voltage regulation, Vs, it is 240 by mod A 0.94. So 240 by 0.94 minus 220 by 220 into 100%. Vs by A minus Vr by Vr in magnitudes. Tell me please how much? How much is that? 16%. 16% voltage regulation we can expect. 16% voltage regulation. So you can choose that correct option as C. Correct option is C. 16%. It's a previous gate question. Previous gate question asked for, I think, 1 mark. Okay. So I'm taking up the next question. Go through this. Is a prospective question in the gate examination. Prospective question means expected question. Expected question in the gate examination, maybe in future. Terms may change and numbers may change, but it is one of the model what you have to treat. One of the model what you have to treat. Go through it. The generalized circuit constants of a three-phase transmission line are A equal to 0.977 at an angle 0.66 degree and B 90.18 at an angle 64.12 degree ohms respectively. If the excitation voltage at no load condition is 132 kV. What do you mean by excitation voltage at no load condition is 132? What do you mean by that excitation voltage? Sending end voltage. Sending end voltage is equals to 132 kV. That's the meaning. Sending end voltage. Then the power loss under this state is dash kilowatts. How much is the power loss in the transmission line in this particular operation? Yeah, tell me. See, A and B are given, that's okay. He said line is operating under no load. Na? Line is at no load. That's the point what you have to identify. Line is at no load. And he mentioned the value of sending end voltage 132. It's line to line magnitude. Line to line sending end voltage magnitude 132 kV. How much is the power loss in this state of operation means at no load? Means he is asking us to know how much will be the value of the no load power loss. How much will be the value of no load power loss? How to calculate this one? No load power loss value. Anybody? What are the various ways of calculating the power loss? Generalized circuit means nominal pi model. It may or may not be Vishnu, may or may not be. Those are generalized circuit constants. That's it. You didn't set the model here. Yeah, can you tell me your answer? How to calculate power loss? What are the various formula available here? So in this case, listen please. Listen all of you. See, calculating power loss in various ways means one way you can say I square into R. Other way you can say voltage across a resistor square by R. But while you are doing these things, I square into R or V square by R, that I should be current in the resistor. I should be current in the resistor, not the sending end current or receiving end current. Not the sending end current or receiving end current. Current in the resistor, you should say. V is a voltage across the resistor. Voltage across the resistor, we should say. But we are unable to find these two. I, we don't know. We know only sending, we are capable to get only sending end current and receiving end current. We don't know how much is the current in the resistor. We don't know how much is the voltage across the resistor. So these formula we can't use right now. But we have one basic formula, very basic formula for the power loss as input minus output. We have a very basic formula for the power loss as input minus output. But as far as the no load is concerned, this number will be 0 and we have to take up only input power as a power loss. Sending end power, that itself is a power loss, we can say. I think all of you getting this word. Clear? So we have to calculate the sending end power of the transmission line under no load condition to calculate the power loss. I will show that in a two-port network model first. Two-port network model. It's a ABCD model of line. Okay. So this is a sending end side. Sending end side we can call. So it's VS phase. This current we have as IS phase. Bar you can keep. Receiving end side open circuit means IR phase bar current is 0. And this voltage we have as VR0 phase bar. No load condition we said. No load condition we have mentioned. VR0 phase bar. Okay. So you write directly. A receiving end power 0, but this PS value will be non-zero. Sending end power will be non-zero because of loss. So I can say no load power loss is nothing but sending end power at no load condition. No load power loss is equals to sending end power at no load condition. What is sending end power formula? Three phase power you have to give an answer. See, listen. In the exam, if he's asking voltage in the TND particularly, if he's asking simply voltage, we should give line to line voltage as your answer. If he's asking voltage, we should give line to line voltage as your answer. If he's asking power, any power, real power, reactive power, maximum power, power loss, whatever it is, we should give three-phase number as your answer. Okay. So I'll say no load power loss in three phase is equal to 3 into sending end voltage magnitude, sending end current magnitude multiplied with cos phi s. That is cosine of angle between Vs phase and Is phase. Cosine of angle between Vs phase and Is phase. What is Vs phase? You know it. 132 by root 3. What is Is phase? That we have to calculate. And we have to substitute here. Cos phi s also we need here. Means we have to deal with angles. We have to definitely deal with angles. We should know how is the angle difference between Vs phase and Is phase. Okay, to calculate this. So I'll say first Vs phase 132 kV by root 3. So it will be 76.21 kilo. So let us consider this itself as a reference. This itself you choose as a reference. Okay, let Vs phase bar chosen as a reference. So you can call this like 76.21 at an angle 0 degree kilovolts. 76.21 at an angle of 0 degree kilovolts. Now, could you please tell me how to calculate sending end current under this no load operation? How to calculate the sending end current under this no load operation? As we know, Is phase bar equals to C into VR phase bar plus D into IR phase bar. IR phase bar 0, so D into IR phase bar 0. And here you get C into VR 0 phase bar. C into VR 0 phase bar. Nothing but C into. What is VR 0 phase bar? Vs phase bar by A. C into Vs phase bar by A. Okay. Next, what is parameter A? Already we know it, right? How much? 0.977 at angle 0.66 degree. But you need C. We need the value of C. What is C given in the data? Didn't mention anything about C. How to calculate it? To calculate that, we have to assume that the line is symmetrical as well as reciprocal. Symmetrical as well as reciprocal. Symmetrical means A equals to B. Reciprocal means AD minus BC equals to 1. From that, you should get the value of C and we have to use it. Okay. So I can say first, the line is assumed as symmetrical and reciprocal. Symmetrical as well as reciprocal. Symmetrical means you call A equals to D. Reciprocal means you call AD minus BC 1. AD minus BC value 1. So let's take now. As AD minus BC is 1, from this you can say parameter C here. You can say AD minus 1 by B. Like this. Okay, so AD it will be 0.977 at an angle of 0.66 degree whole square minus 1 by parameter B is 90.18 at an angle 64.12 degrees. 64.12 degrees. Yeah, you calculate its magnitude and angle. Carefully calculate it. That angle is very, very important for us. Angle. Yeah, you'll get a C. Magnitude 5.626 into 10 power minus 4. Angle is coming like 90.1971. More. That's a C. That's a C. Now you can go with the sending end current IS phase bar by using this equation. Now that IS phase bar will come like C. This value we have to substitute. C into Vs phase bar by A. What is Vs phase bar? It is 76.21 kilo at an angle 0 degree by parameter A 0.977 angle of 0.66 degree. That's it. Okay. So you take this magnitude and angle carefully. You take that magnitude and angle. That is 43.886 degree. Sorry, 43.886 amperes. Angle will come to be 89.5371. 89.5371 degree in terms of amperes. I'm saying you Ashish, they will give the value of C in the examination. Just follow the procedure, whatever I am saying you. Okay, I am not given C in the what we call question. In the examination, they will give the value of C so that the calculations will be simple. Yeah, let's go with cos phi s value now. Cos phi s, because we need to get this value, right? This is our final answer. Cos phi s, cosine of angle between Vs phase bar and Is phase bar. Cosine of angle between Vs phase bar and Is phase bar. See, you can say cosine of angle between. What is Vs phase bar angle? 0. Vs phase bar angle is 0. Is phase bar angle 89.537 degree. 89.5371 degree. So cos 89.5371 degree. So it will come to be 8.079 into 10 power minus 3. 8.079 into 10 power minus 3. Yeah, please do it quickly. Is it leading or lagging? That's a question now. Is it in leading or lagging? This power factor. How we can decide is it in leading or lagging? Just by checking the current angle with respect to voltage angle. Checking the current angle with respect to voltage angle. If the current angle is more compared to voltage angle, I will say it is leading. If the current angle is less compared to voltage angle, I will say it is lagging. So current angle 89.53 degree, voltage angle 0 degree, current angle is more compared to voltage angle. So this will be in leading. That will be in leading. So finally, we try to calculate the no load power loss three phase value. So 3 times Vs phase 76.21 kilo. Okay. So Is phase 43.886. Power factor 8.079 into 10 power minus 3. In terms of watts. In terms of watts. Yeah. Please get this. It will come to be 81.062. 062 kilowatts. 81.062 kilowatts. Approximately 81 kilowatts you can choose. So check in what manner is asking. Kilowatts. Okay. Kilowatts means you have to type this number 81.062 in the blank. In the blank, you have to type this number 81.062. They will give some flexible numbers. I am saying you should be. Just follow the procedure. Just follow the procedure, please. Without doing this type of problem, you can't get the clarity of calculating no load power loss. So I can't avoid it in teaching this type of problem. Yeah. Receiving end, there is no problem of power factor. There is no power factor at all at receiving end side. Current is 0. What's the meaning of receiving end power factor now? Receiving end current is 0. How we got Is phase formula that we have discussed in previous class. Please come with the class, come to the class by going to the previous class notes thoroughly. Yeah. Yeah. So the next topic what we are going to discuss here is power equations, particularly steady state power transfer equations of the power transmission. Steady state power transfer equations of transmission. Okay, have a break for 10 minutes. So after break, we will be continuing with the topic that is very, very important one for the examination. Okay, 10 minutes break. So I have resumed audio video on screen. Resumed the audio video on screen. So please kindly take up the next heading, which is very, very important for GATE examination as well as ESE examination also. Steady state power transfer equations. Steady state power transfer equations of transmission line in terms of ABCD. In terms of ABCD. Okay, yeah, see. See, first of all, we have a transmission line connected between two buses. I am showing like this. Is the transmission line wire connecting two buses. Yeah, so these are the two buses we have, sending end side, and it's a receiving end side bus. You can say, yeah. See, this transmission line we are going to represent in the form of ABCD parameters. Transmission line we are going to represent in the form of ABCD parameters. See, sending end side, you may not have generator directly. You may not have the generator directly. Some network, whatever it is, some network is supplying to this bus, feeding to this bus. Okay, but I will be showing that as a generator. But you should know that it's not a directly connected generator. Some system is feeding to this. That's what the thing you have to understand now. Some system is feeding to that. Right. So this is a source generator, we can say. Next, at the receiving end side, you may not have a direct load connection. It is connected to, yeah, is it audio clear? Audio. Yeah. Fine. Yeah. So at this receiving end side, generally number of lines are connected. For each line, we have some load. The total, I am combining to this place. Combining that to this place simply as a load indication. Clear? Fine. Next thing. Sending end side notations I am saying you. It is VS bar, IS bar. Receiving end side notations, VR bar, IR bar. Sending end side, VS bar, IS bar. Receiving end side, we have like VR bar, IR bar. Okay, now, our aim right now in this present discussion is to find out real and reactive powers injected to receiving end bus. Our aim is to find out the real and reactive powers injected to receiving end bus. Means I'll say first of all complex power SR, which is nothing but PR plus JQR. So we have to know the real and reactive powers injected to the receiving end bus. Fine. Next. Listen. See, I will be taking this VR as a reference. Receiving end voltage I will take as a reference. So I will say VR bar is like mod VR at an angle 0 degree. VR bar I am taking like mod VR at an angle 0 degree. How is this VS bar? Magnitude, let me say VS. My question is, how is the sending end voltage with respect to receiving end voltage? Is it lagging or leading? How is that sending end voltage with respect to receiving end voltage? Is it lagging or leading? Leading. How you can say VS is in leading with respect to VR? How you can say VS is in leading with respect to VR? That's what we got from short transmission line phasor diagram. In the short transmission line phasor diagram, we have drawn that phasor diagram where we have shown that VS is in lead with respect to VR. All of you getting that? So I can say VS bar leads VR bar by an angle delta, let us say. Delta. The delta is going to be called generally as displacement angle. Displacement angle between two phasors. Displacement angle between two phasors. So I'll say it is delta. Delta. So when this Vs is in leading with respect to Vr means from the phasor diagram, particularly if the X by R ratio of system is very, very large, means X by R ratio of transmission line is very, very large, we can say. So in bracket, I can say, provided that X by R of line is large. X by R of line is a large value. X by R of line is a large value. Okay. Now, what is this complex power SR equation in terms of this voltage and currents? In terms of these voltage and currents, what is the complex power equation for SR? That's something we have to learn. Okay. So many people might be having a doubt in your mind that we will be taking that complex power equation as V into I conjugate, V bar into I bar conjugate. Why you are taking like that? Why can't we take V conjugate I? Why can't we take simply V bar I bar? Why can't we take V bar conjugate I bar conjugate? This is some type of doubt you have in your mind. Let's clear about the complex power equation. Yeah. So I'm saying in the next slide. Next slide. Complex power equation. Complex power equation. See this. For example, this is one bus bar. This one bus bar connected to some power network. At this bus, voltage is V bar. Current injection, we know it is I bar. At that bus, voltage is V bar. Current injection is I bar. Now, you try to find out complex power S here. Try to find out the complex power S. That S is equals to V bar into I bar conjugate is a general formula what we will use. S equal to V bar into I bar conjugate. Why you are using this? Why can't we use V bar I bar? Why can't we use V bar conjugate I bar conjugate? Why can't we use V bar conjugate I bar? Why you are using only first one? Why we are not using these three? Why we are not using remaining three? Why we are concentrating only on VI conjugate? Okay. To explain about this, to learn about it, I am taking a simple network, single phase network, simple single phase network. From that, I will try to tell you why you are considering it. Okay. Yeah. See this. For example, I have one AC voltage source here connected to a RL load. Connected to an RL load. RL load. This voltage I am saying V bar. Current here is I bar, I can say I bar. And this load is having an impedance. Z mod Z at an angle theta or phi, whatever it is. This load might have an impedance like mod Z at an angle phi. Mod Z at an angle phi. That's the load. Tell me, this mod Z at an angle phi you can write like mod Z cos phi plus J times mod Z sin phi. And what's the resistance value of the load? Z cos phi. What's the reactance of the load? Z sin phi. Resistance of the load is Z cos phi, you can say. Reactance of this is Z sin phi. Resistance is Z cos phi, reactance is Z sin phi. Like that you can say. Okay, let voltage V bar. Just I'll say V bar voltage is equal to mod V at an angle theta. V bar is equal to mod V at an angle theta. How is I bar now? Anybody tell me please, how is I bar? I bar. I bar. Vs and Vs bar both are same. Whenever I want to write magnitude, I will keep modulus. Else if I write simply Vs or Vs bar, both will be same. Vs is having some magnitude and angle. Vs bar also having some magnitude and angle. I bar using. So it is V bar by mod z at an angle phi na. So that V bar is like mod V at an angle theta by this is mod z at an angle phi. V bar mod V by mod z you can get here current magnitude. Mod V by mod z current magnitude. Angle will be theta minus phi. Angle will be theta minus phi. Mod V by mod z, angle will be theta minus phi. Clear? That's I bar. So this point voltage is V bar we said. Point voltage is V bar. Now, next, listen please. Listen please. Okay, now we will take in this way. First, what is the real power consumed by the load? We have a resistor. We have a resistor carrying some current. Resistor carrying some current. What is the real power drawn by the load? I square R. Magnitude of current square into resistance. That's the real power consumed. Let's write. Real power consumed. Real power drawn by the load. Load real power consumption. Like that also you can write. P is equals to magnitude of current square into resistance. What is magnitude of current? Mod V by mod Z whole square. Resistance is mod Z into cos phi. So mod Z will be cancelled out and you will get this like mod V square by mod Z into cos phi. Mod V square by mod Z into cos phi. That's the load real power. What's the load reactive power Q? Load reactive power Q. Tell me please, load reactive power Q. That is current square into reactance. Na? Current square into reactance. What is current square? Mod V by mod Z whole square. Reactance is what? Mod Z into sin phi. So I can get this like mod V square by mod Z into sin phi. Mod V square by mod Z into sin phi. Yeah, listen please. Listen please. See, actually, whatever the load we have, that load is absorbing a real power or taking a real power of mod V square by Z into cos phi. Mod V square by Z into cos phi. And the load is taking a reactive power of mod V square by Z into sin phi. Mod V square by Z into sin phi. Please listen. Please listen. Whichever the equation you choose with this V bar and I bar, whichever the equation you choose with this V bar and I bar, that equation should tell that the real and reactive powers are these numbers, because these are exact numbers, right? This is an exact value of real power consumed. This is an exact value of reactive power consumed. Whatever the equation you take in terms of V bar and I bar, that equation should tell the real power as V square by Z cos phi, reactive power as V square by Z into sin phi. So all of you understanding this, what I am saying? It's not instantaneous power. We are talking about real and reactive powers here. It's not instantaneous. Yeah. Can I move? Okay. So now let's take in terms of V bar and I bar, let us take V bar I bar as complex power equation. Let us take V bar I bar. After taking that, if it is satisfying, it's okay. If it's not satisfying, that is not the correct equation to be used in terms of V bar and I bar. So I can say first let S equals to V bar into I bar. That's it. Now you can take V bar mod V at an angle theta, I bar mod V by mod Z at an angle theta minus phi. And we'll get this like mod V square by mod Z. Angle is 2 theta minus phi. So you take real part, mod v square by mod z cos of 2 theta minus phi plus j times mod v square by mod z sin of 2 theta minus phi. Sin of 2 theta minus phi. Clear? Now you take what is the exact real power? What's the exact real power? V square by z into cos phi. But what this equation is saying about real power? V square by z into cos of 2 theta minus phi, right? Real powers has not matched. So this equation will not give or will not represent the exact values of real and reactive powers. So that we should not use V bar into I bar equation. All of you understood the comment? All of you understood that comment? This equation is not saying the exact values of the real and reactive powers, so that we can't use this. We can't use this for the calculation of the real and the reactive powers. For example, I'll take conjugate. So V bar conjugate, I bar conjugate, let us take them. Then here you will get minus theta. Here you will get minus theta plus phi. And what you get here? Phi minus theta, na? Minus 2 theta plus phi you will get. So minus 2 theta plus phi. Minus 2 theta plus phi. Again, it is not saying exact value of real power. Again, this also not saying the exact value of real power. So V conjugate into I conjugate also not going to represent that. V conjugate, I conjugate also not going to represent exact values of the real and the reactive powers. Okay, now let's take V bar into I bar conjugate. V bar into I bar conjugate as the second one. Let S is equal to V bar into I bar conjugate. So now you take this S here. V bar is mod V at an angle theta. I bar conjugate, if you write, I bar conjugate, if you write, mod V by mod Z, mod V by mod Z, an angle, you know, it is a theta minus phi. For this, you have to apply conjugate. So you take up this, you have mod V at an angle theta. So it is mod V by mod Z at an angle phi minus theta. So theta will be cancelled out and you'll get this like mod V square by mod Z angle phi. So after taking this one, you can have mod V square by mod Z cos phi plus j times mod V square by mod Z sin phi. Mod V square by mod Z sin phi. Is it representing exact values of real and reactive powers? Is this equation representing exact values of real and reactive powers? Yes or no? Yes. Real power V square by Z into cos phi. Exact value is also same. Reactive power V square by Z into sin phi. This also same. So this equation is representing the exact values of the real and reactive powers. That's why we have to use only V bar into I bar conjugate for the complex power calculation. Okay. So let me write that comment in the next slide. Write that comment in the next slide. Complex power equation S equal to V bar into I bar conjugate. Okay. So it represents the exact values of real and reactive powers. Real and reactive powers. It represents exact values of real and reactive powers. Okay. Just listen to my question. I will ask some very, very silly and simple question. Just tell me the answer. Current. Will you give direction of current or will you keep current at one point? Will you say that current at one point or will you give the direction of current? Tell me all of you. So definitely we have to give the direction of current, right? Definitely we have to give the direction of the current. Okay, fine. Voltage. Will it tell voltage at 1 point, or can we give the direction of voltage? At 1 point. 1 point means from the point to reference. From the point to reference, we can measure the voltage. Next one, simple. Complex power. Complex power. Will you give direction of complex power, or will you tell complex power at 1 point? Complex power, will you give direction or at 1 point? Definitely direction has to be given, not at 1 point. Not at 1 point. Definitely we should give the direction of the complex power, not both. Not both. Listen to me. Whenever you say complex power, you should tell in which direction the complex power is flowing, in which direction the real power is flowing, which direction the reactive power is flowing. Okay. See, if you are calculating complex power by using V bar into I bar conjugate, V bar into I bar conjugate, that will give you complex power flowing in the direction of current what you have chosen. Irrespective any direction you take current, you calculate V into I conjugate. Complex power is a complex power flowing in that particular direction of current what we have chosen in the network. Okay, so real and reactive powers flowing in the direction of current. Real and reactive powers flowing in the direction of the current. Okay, next. For example, if I use V conjugate into I, what will happen? For example, if you use the V conjugate into I, what will happen? Tell me. So same thing I have copied to the next slide. Just listen. Let third one. Let S is equals to V conjugate into I. Means V bar conjugate into I bar. So I don't have a conjugate for this. I have a conjugate for this one now. I have a conjugate for this one. And this will be minus theta, and this will be theta minus phi only. This is theta minus phi only, and it will be minus phi, and here you will get minus. Like this only. Again, it is saying same real and reactive powers. Numbers are same. I need your concentration thoroughly here. Why do we consider V as a phasor? What's the doubt you have, Vishnu, in that? What's the doubt you have? What's the doubt, Vishnu? Yeah, tell me please. A magnitude is same, but directions are a bit different. Just look here. See, this is a circuit on which we are doing this calculations. This V bar, and this I bar, and this is a load. See, if you are using, just listen to my words. If you are using V conjugate into I, what this equation is saying is load is absorbing a real power of V square by Z into cos phi. Load is absorbing a real power of V square by Z into cos phi. Correct. And what is saying is load is absorbing a reactive power. Of minus V square by Z into sin phi. Means load is delivering reactive power of V square by Z into sin phi. Load is delivering a reactive power of V square by Z into sin phi. But in the previous equation, what we are saying? Load is absorbing a reactive power of V square by Z into sin phi. Numbers are same. V into I conjugate is saying that, look here. V into I conjugate is saying that load is absorbing the reactive power. V conjugate into I is saying that load is delivering the reactive power. Which is correct here. Load is absorbing reactive power or load is delivering reactive power. What type of load you have here? Inductive load here. Inductive load here. Tell me please. Load is absorbing reactive power or delivering reactive power? Means inductor. Inductor what we have? Absorbing or delivering? Absorbing. Okay. Absorbing. Absorbing. Is it convention or fact? Is it convention or fact? Yeah, convention. It's not fact. It's not fact. It is convention. Listen to me, please. So according to the convention, what we studied long back in the TND, right? According to the convention, what we have taken long back in the TND, we said that inductor is absorbing the reactive power, capacitor is delivering the reactive power. So as we are keeping inductor here, it should absorb the reactive power. In that way, I am choosing the equation V into I conjugate. So whenever you are saying complex power equation as V into I conjugate, not only this definition, we should say the convention also as inductor absorbing the reactive power, capacitor delivering the reactive power. Based on that convention, complex power equation is V into I conjugate. That's the link up. Yes, I don't know whether you are clear or not. Are you clear about this? L absorbs reactive power. C delivers reactive based on that convention. Okay, so now I'll tell. Listen to me. I'll tell. This is a point where I might be checking your understanding. Can I use complex power equation V conjugate into I or not? Can I use V conjugate into I? Can I use V conjugate into I? Yes or no? Yes or no? Yes, we can use, but you have to change your convention. Yes, you can use, but you have to change your convention. Simple. Yeah. Convention you have to change. Good. That's it. But universally, this convention the people will follow. That's why always we will be taking up V bar into I bar conjugate. Okay, it's a universal convention. Universal convention. Let me continue with our actual discussion now. This is a place where we have started our discussion and we have gone for the complex power equation and all. Now, SR, what you can write here? SR, what you can write? VR bar into IR bar conjugate. VR bar into IR bar conjugate. You have to observe that current and complex power both are taken in the same direction. So, transmission line, complex power injected at receiving end side. Complex power injected at receiving end side. SR is equals to VR bar into IR bar conjugate. VR bar into IR bar conjugate. Okay. VR bar into IR bar conjugate. Now that IR receiving end current, I will try to replace in terms of voltages by using ABCD equation. As you know already, Vs equals to AVR plus BIR. I'll keep bar here also. We are doing only per phase analysis here. I no need to mention always these are phase values. These are phase values only we are taking up in the calculations. Now you can take this IR bar from this equation, IR bar, and get like Vs bar minus A into VR bar by B. Vs bar minus A into Vr bar by B. Okay. Now already you know Vs bar. Vs bar you can write mod Vs at an angle delta. Vs bar you can write it as mod Vs at an angle delta. A mod A at an angle alpha. Vr bar mod Vr at an angle 0 by B mod B at an angle beta. Mod B at an angle beta. Don't combine the things here, Vishnu. Don't combine the things here. Just look. Go through the thing. Whenever that point comes, I will discuss about it. So I will be simplifying this like mod Vs by mod B. Mod Vs by mod B. Angle is delta minus beta. Next magnitude. Mod A by mod B, mod Vr. Angle will be alpha plus 0 minus beta. This is IR bar. Take up conjugate for that. IR bar conjugate you take. Then we will go for SR equation. IR bar conjugate, if you are applying, magnitude will be as it is, but angle will be getting negative sign. IR bar conjugate. Mod Vs by mod B. Angle will be, you get beta minus delta here. Minus mod A by mod B. Mod Vr. Angle you are going to get like beta minus alpha. Beta minus alpha. Now that IR conjugate you substitute here so that you can get SR. Complex power SR. SR equals to Vr bar means mod Vr at angle 0. IR bar conjugate means you can copy this. Yeah, already applied conjugate. So you take this multiplication. So you can have Vs, Vr, mod Vr by mod B. Angle we get beta minus delta minus mod A by mod B, and you have mod Vr squared angle beta minus alpha. Beta minus alpha. Because this angle is 0, so it makes no difference for the angle, but only that mod Vr gets multiplied for all. This is SR. From this, you take the real part and the imaginary part, which will give you real power and reactive power injected to receiving end bus. Real and reactive powers injected to receiving end bus. Yeah, so we take a real part of that, real power injection to the receiving end bus. PR is equals to, real part means cosine of the angles, right? Mod Vs, mod Vr by mod B, cos beta minus delta. Mod Vs, mod Vr by mod B, cos beta minus delta, minus mod A by mod B, mod Vr square, cos of beta minus alpha. Cos of beta minus alpha. That's a real power. Next, reactive power QR you can write. Mod Vs, mod Vr by mod B, sin beta minus delta, minus mod A by mod B, mod Vr square, sin beta minus alpha. Sin beta minus alpha. So these are the real and reactive powers injected to receiving end bus. real and reactive powers injected to receiving end bus. Yeah, three phase just multiplied by 3, Pratyusha. Multiplied with 3, that's it. Doubt in that. Just multiplied with 3 will. Okay. Yeah. So next, see, till now in the complete what we call derivation from this SR equals to VR into IR conjugate and all, we have not taken anywhere three phase. This complete calculation is with respect to per phase only. Means whatever that mod VS and mod VR you have in this one, these are per phase values. Per phase values. So obviously PR and QR will be per phase real and reactive force. Yeah. So as we know, mod VS and mod VR in above equation, the above set of equations, sending end voltage and receiving end voltages are per phase values. Per phase values. So obviously, real and reactive powers PR, QR will be definitely per phase. Definitely per phase. PR and QR will be per phase. Yeah. Next thing. For example, if you want to get three phase power, what you have to do? Just you have to multiply this with 3. Getting three phase power, we have to multiply this with 3. Listen please. All of you, stop right. Three phase real power equals to 3 Vs phase VR phase by mod B cos beta minus delta minus 3 into mod A by mod B VR phase square cos of beta minus alpha. So in the first term for three phase, you will get 3 Vs phase VR phase. The first term you will get 3 into Vs phase VR phase. Second term you will get 3 into VR phase square. 3 into VR phase square. First term 3 into Vs phase VR phase we have na. That I will write as root 3 Vs phase into root 3 VR phase. That root 3 into Vs phase is Vs line to line magnitude. Root 3 VR phase is VR line to line magnitude. There is no meaning of delta. There is no meaning of delta saying that per phase voltage equals to line voltage. There is no meaning of that. We are discussing about transmission lines. In case of transmission lines, like this, if you say, okay, A, B, C wires, conductor voltage you say phase, line to line voltage, V line to line equal to root 3 times of phase voltage. That's it for the transmission lines. There is no and nothing to recall the delta connection here. Okay, right. So you see this 3 into VR phase square, root 3 into VR phase magnitude, you can write whole square. So that will come VR line to line square. Done? VR line to line square. Means my interest is to tell you now, if you are attempting to get the three phase real power, you will get 3 Vs phase VR phase here. You will get here 3 VR phase square. 3 Vs phase VR phase you can replace with Vs line to line, VR line to line. Vs line to line, VR line to line. 3 VR phase square you will get as VR line to line square. VR line to line square. Means directly if you substitute the line to line voltages here, you will be getting three phase powers, right? You will be getting three phase powers. Have you understood this point, what I said? Have you understood this point, what I said? If directly you keep line to line voltage instead of the per phase, we are going to get the three phase power. But impedances will be per phase only. We are not disturbing impedances. Very simple, Dinesh. This is per phase power. multiply with 3 will give 3 phase power. Multiplying the 3 is converting this line to line voltages product into, sorry, per phase voltage product into line to line. 3 VR phase square, we are replacing with VR line to line square. That's it. Why you are bothering about impedances now? Okay. So I can say, if you keep directly VS and VR values as line to line RMS values, then obviously real and reactive powers will come 3 phase. That will come 3 phase powers. Yeah. Right. Next thing. See, actually, from these two equations again, which are constants and which may vary with respect to load. With respect to load, which values may vary in the sense, particularly voltage magnitude and associated angle delta. Voltage magnitude and associated angle delta. These values will vary. Remaining, whatever the parameters A and B we have, those are constants. Means real power PR is a function of mod V and delta. PR is a function of mod V and delta. QR also a function of mod V and delta. Okay. So you can write now powers. PR function of mod V comma delta. QR also a function of mod V comma delta. PR and QR are functions of mod V comma delta. Where that mod V comma delta are going to be called as states of the system. Mod V comma delta, these are going to be called as states, state variables, you can say. States of the system. States of the system. Beta and alpha are constants, right? For a given ABCD parameters, beta and alpha are constants. ABCD parameters are constant. With respect to load, it won't change, na? Yeah, let's move. How these two functions looks for us, whether these are linear or non-linear. Because of this existence of cosine and sine. Cosine of beta minus delta, sine of beta minus delta, obviously these two equations are non-linear algebraic equations. These are going to be called as non-linear algebraic transcendental equations. Transcendental equations. Because of that existence of sine and cosine, you take any order of differentiation. Any order of differentiation, still some function will exist. Still some function will exist. That's the meaning of transcendental. Transcendental. Repetitive differentiations we are going to get. Next. So these are some comments regarding the power equations. I think some of them we studied in the load flow also. Now let's take up some terms here. First term I'm going to take up here. What is differentiation of PR with respect to delta? First term. Dou PR by dou delta equation I want. First. As a first. Second one. Dou PR by dou VR equation I want. Next one, reactive power differentiation terms. Next one will be reactive power differentiation terms. Dou QR by dou delta term I want. Fourth one will be dou QR by dou VR. Dou QR by dou mod VR we want. Look at this first. Look at this. What is the differentiation of real power with respect to delta? Yes, Dinesh. Yes. What is the differentiation of real power with respect to delta? Simple. Let's just look back. PR differentiation with respect to delta. Only one term is having delta. Second term does not have. So second term differentiation 0. Leave it out. VSVR by B, cos differentiation, minus sign, minus sign of beta minus delta. Again, beta minus delta differentiation with respect to delta will give -1. Minus will be cancelled. So dou PR by dou delta will be like mod VS mod VR by mod B sin beta minus delta. Okay, so cancellations will happen. Cosine differentiation is minus sign, but again beta minus delta differentiated with respect to delta will give -1. Minus will cancel. What is dou PR by dou VR? Dou PR by dou VR. Look here. So VS by B cos beta minus delta minus A by B 2 VR cos of beta minus alpha. So I can say mod VS by mod B cos beta minus delta minus 2 times mod A by mod B mod VR cos beta minus alpha. Like that you get dou PR by dou VR. Dou PR by dou VR. Dou PR by dou VR. Next. Dou QR by dou delta. Dou QR by dou delta. VS VR by B. Sign differentiation. Cos beta minus delta. Again, with delta we differentiate. You get minus. Next term differentiation is 0 with respect to delta. So I can say VS VR by B. Sign differentiation is cos. Beta minus delta differentiation will give minus. So minus VS VR by B cos of beta minus delta. Next, dou QR by dou V. Dou QR by dou V. VS by B sin beta minus delta minus. And you get 2 times like that. Okay. So you get VS by B sin beta minus delta minus 2 times mod A by mod B mod VR sin beta minus alpha. Sin beta minus alpha. Yeah. Like this, we'll get these 4 differential terms. 4 differential terms. Listen now. Assumption what I am making. X by R ratio of system is very high. That's the assumption. If X by R ratio of system is very high, X by R is large means, obviously beta will be close to 90 degree. X by R ratio of system is very large means, beta value will be very close to 90 degree. Yes or no? Yes or no? Yeah. So beta will be very, very close to 90. And you assume that delta is a bit small angle, like 10 degree, like that. Delta is a bit small angle, might be 10 degrees. So what is this beta minus delta? Close to 80 degree, I can say. Approximately, that beta minus delta is 80 degree. 80 degrees. Okay, next. This beta minus delta is again 80 degrees. And you see alpha close to 0 degree, na? Alpha will be close to 0 degree, beta close to 90. So this angle will be close to 90 degree, approximately. This angle will be very close to 90 degree. Angle of parameter B is beta, na? Angle of parameter B. Okay, next. Here also. This is close to 80. Close to 80. This is close to 90. Fine. Now, you see this. Sin 80. Sin 80. Close to 1. Sin 80 degree. Close to 1. Okay. Cos 80. Close to 0. Cos 90. 0. For high X by R ratio system. For high X by R ratio system, we are discussing. Kindly understand. Sin 80 close to 1. Cos 80 close to 0. Cos 90 also close to 0. Means this dou PR by dou VR number is negligibly small compared with dou PR by dou delta. Dou PR by dou delta. All of you understood this comment? All of you understood this comment. So dou PR by dou delta is very, very high. Compare it to dou PR by dou VR. Dou PR by dou delta is very, very high. Compare it to dou PR by dou mod VR. And you see here, cos 80 close to 0. This is close to 0. Next year, sin 80 close to 1. Sin 90 close to 1. It is 1 minus 2. It's 1 minus 2. It's negative value, but it's very high. Negative value, magnitude will be very high. Means you can say dou QR by dou mod VR very, very high compared to dou QR by dou delta. Dou QR by dou mod VR dou QR by dou mod VR is very, very high compared to dou QR by dou delta. Okay, we assumed that beta is close to 90. Delta is a small angle. Delta is a small angle like 10 degree. So beta minus delta will be close to 80, we have assumed. See, based on all these assumptions, what we have made for high X-bar ratio systems. For high X-bar ratio systems, the real power flow is mainly dependent or more sensitive to delta variation as compared to the voltage magnitude variation. Real power is more sensitive to delta variation as compared to voltage magnitude variation. Reactive power is more sensitive with respect to voltage magnitude variation as compared to the delta variation. That comment we can make for a high X-bar ratio system. High X-bar ratio system. Okay, so I will move to the next slide to write it. For high X-bar ratio systems, high X-bar ratio systems, P is more sensitive to delta variation and less sensitive to mod V variation. Next, Q is more sensitive to mod V variation and less sensitive to delta variations. Less sensitive to delta variations. Yeah, stability analysis also we have discussed this one almost. Not stability, I think in load flow. In load flow, we might have discussed about it. Okay, let's move. See, my aim is to find condition for the maximum real power injection to the receiving end bus. Condition for the maximum real power injection to receiving end bus, or else you can say condition for maximum power transfer. Condition for the maximum power transfer. So condition for maximum power transfer with respect to which variation we have to find now? With respect to delta, because real power is more sensitive to delta variation. Okay, so I will show in the next slide condition for maximum real power transfer. Maximum real power transfer. Okay, so PR maximum. PR max in bracket you write PR max. This we discussed in stability. Same point. First you write PR versus delta. It's a non-linear shape. PR versus delta is a non-linear shape. If it's a non-linear curve or non-linear variation, non-linear curve, or we can say non-linear variation. What is the condition for maximum? First differential term should be equals to 0. Condition for PR max is dPr by d delta is equal to 0, or dou PR by dou delta also you write. Anything. dPr by d delta is equals to 0. What is dPr by d delta? Already we have derived. That is Vs Vr by mod B sine beta minus delta. So this will come Vs Vr by mod B sine beta minus delta is equal to 0. In this complete calculations, we will be assuming that voltage magnitudes are constants. We will be assuming that voltage magnitudes are constant. So this is constant for us. This constant that you can send to the other side. Anyhow, 0. The condition what we get is sine of beta minus delta is equals to 0. Condition will get like sine of beta minus delta is equals to 0. Now what is beta minus delta from this? Beta minus delta, what you can get? 0 degree. Beta minus delta is equals to 0 degree is one option. From which you can say delta is equal to beta. Means whenever the angular difference between the bus voltages is equals to beta, angular difference between the bus voltages is equal to angle of parameter B. Angle of parameter B. At that point, we may touch the maximum power transfer. We may touch the maximum power transfer. Now, simply you try to find out the PR maximum value by keeping this delta equals to beta in the PR equation. Now, the value of PR maximum is nothing but PR value by keeping delta is equal to beta. PR value by keeping delta equals to beta. So already you have PR equation, this one. This is a PR equation we have. Right. Just observe. So it's a PR equation. So simply in place of this delta, we keep beta. So it is cos 0. So it is 1, you can say. And you can write PR max. You can write PR max, PR maximum as Vs into Vr by mod B minus, you can have mod A by mod B mod Vr square cos of beta minus alpha. This is that maximum power transfer capacity. Maximum power transfer capacity. Yeah. You just try to find how is the reactive power QR. How is the reactive power QR in this operation? Means during maximum power transfer condition, how is the reactive power QR? Is it positive or negative? That we have to know. Okay, that's it. QR value during PR max condition. QR value during PR maximum condition. So you have to find that QR by keeping the delta equals to beta. That's it. By keeping the delta equals to beta, you have to find out the QR. So already you have that QR equation. This we will use now. This equation we will be using. QR equation. Yeah. This is the equation of QR. Now we should keep simply delta is equals to beta here. So this is that substitution we are making. So sine beta minus beta, sine 0, that is 0. 0. So first term will vanish completely and you get only second term now. Minus mod A by mod B, mod VR square, sine beta minus alpha. Like this you can get. Minus mod A by mod B, mod VR square, sine of beta minus alpha. This is QR. But one thing, you are observing some minus sign in front of this, right? You are observing some minus sign in front of this one. We try to check whether this QR is negative during this P maximum condition, or is there any possibility of getting that number as positive? Okay, just check this quickly. Mod A by mod B, we have to check this number. Already we have minus sign in front of that. If you check this number, that will tell you whether this whole number is becoming positive or negative. Mod A by mod B, positive. Mod VR square, positive. Sine of beta minus alpha. See, what is that maximum value of beta minus alpha you can experience? Maximum value of beta minus alpha, how much you can experience? See, beta maximum is 90 degree. Beta maximum is 90 degree, alpha minimum 0. So maximum angle will be 90. So it will be less than or equals to 90. Less than or equals to 90, but very, very high compared to 0 degree. Very, very high compared to 0. Why? In the sense, beta minimum 50 degree. Beta minimum 50 degree. Alpha 10 degree maximum. 50 minus 10, 40. Very, very high compared to 0. So in the span of 0 to 90, this is positive only, na? Sine value. Sine value will be positive. So this whole number, what you keep inside the bracket is positive, but in front of that, we have a minus sign. In front of that, we have a minus sign. So one thing what we can confirm is QR is definitely negative during the maximum power transfer condition, right? So QR is negative during PR maximum condition. This we can confirm. QR is negative value during maximum power transfer condition. Maximum power transfer condition. Okay, let's say here, for example, at this receiving end bus, what we are talking, we have a maximum real power injection, and during this maximum real power injection condition, reactive power value injected is negative number. Reactive power value injected is negative number. So whatever the load you have here, it is absorbing negative reactive power. That load is absorbing negative reactive power. See, load is absorbing negative reactive power means, is it going to take that, absorb that reactive power or deliver that reactive power? Whether that load is going to absorb the reactive power or deliver the reactive power? Delivers the reactive power. Okay. So the condition what you have to make here is, load should have a capability of delivering the reactive power to satisfy the PR maximum conditions. Okay. So I can say load must have a capability of delivering the reactive power. Then which type of loads will deliver the reactive power? Capacitive loads will deliver the reactive power. That implies load must be capacitive in nature. Load must be capacitive in nature. Load must be capacitive in nature. Okay. Yeah, pure resistive load can attain maximum power it is not the maximum power what we have written. It is not that maximum power what we have written. Okay. Let me tell you. So PR versus delta we will try to plot. PR versus delta we will try to plot so-called power angle curve. Power angle curve. By using the power angle curve, we will come to know in which region the system is stable, which region it is unstable. These comments we will make. Which we might have studied in stability or we might be studying in stability analysis later. Okay. Yeah. So let's say here. Power angle. Power angle curve. PR versus delta. PR versus delta. Very simple thing. Very simple thing. Just listen. Already we have PR equation. That let me copy once. This one. This is the equation of PR we have. Just look at this one. First, I'll take delta axis as x-axis. Almost similar to the voltage regulation curve which we have drawn. Procedure is similar, but don't say that voltage regulation curve and power angle curve are same. That's not the thing what I'm saying. Mathematically, some similarities are there. First, it is a delta axis. On this y-axis, we should build up the power. We should build up the power. Cos delta we'll get like this. Cos delta. Okay, this is cos delta. Cos beta minus delta means it has to be shifted by an angle of beta. It has to be shifted by an angle of beta. Maybe I can say like this we can experience. This is cos of beta minus delta. Cos of delta minus beta or cos of beta minus delta, both will be same. Both will be same. Next, this red color curve, multiply with Vs VR by mod B, will have some peak. The peak value was Vs VR by mod B. From this curve, we should subtract this second term. We have to remove the second term from that, which is mod A by mod B mod VR square cos of beta minus alpha, which is independent on delta. It's a constant term with respect to delta. Okay. So subtracting the term means this red color curve what we have shown, it will be coming down. That red color curve will be coming down. Coming down in the sense, it may fall. Look here, this. It may fall above the origin sometime. It may fall below the origin also. It may not pass through the origin. The curve may fall above the origin or it may fall below the origin. Both chances are there. It may not pass through the origin. We are discussing about exact power angle. Okay. So I will be taking up that power angle curve as a whole in the next slide. I'm taking up the power angle curve. Kindly look. So it's a delta axis. I'm showing delta axis, and it's a power axis. Power axis and delta axis. Right. So the power angle curve may come. I am taking the power angle curve something like this. So I'm taking the power angle. It's not pass through origin. It's little above the origin. That's the thing. And this 0 degree, of course, 0 degree. And this is a point at which we are getting the maximum power. Okay. And at what angle we are touching the P maximum? Delta is equals to beta. Because at delta equals to 0 degree, subtracting second term, at delta equals to 0 degree, that power is not coming as 0, right? If you keep delta equals to 0 in this equation, you get Vs VR by B cos beta minus mod A by mod B mod VR square cos of beta minus alpha. We are not sure that that number is 0 for delta equals to 0 degree. That's why it may not pass through origin. But most of the times in the stability analysis or even in the textbooks also, you can see that the power angle curve is passing through origin. Power angle curve is passing through origin most of the times. That is the approximate curve. That's the approximate curve. That also we'll discuss. Yeah. So at what condition we are getting the maximum power? For an angle of delta equals to beta, we are getting that. For an angle of delta equals to beta. Yeah. Next thing. Where is 90-degree location? For understanding only, we are not doing anything with that 90-degree now. That 90-degree will be at this place. Because your beta will be less than 90, na? Less than 90. So your 90-degree will be at this place. Okay, fine. Next thing. So I'm taking up two case studies now. Two case studies to tell whether the system is stable or unstable. That's it. Simple, very simple case studies I'm taking up. Case 1, case 2. Case 1. Source. We have a line with some series impedance of Z. Is some load. It's not a direct load as I said. It's not a direct load. It's a network connected. It's a big network connected to that. That network is demanding power from the line connected. Demanding the power. And this load is taking a real power of P load. Line is injecting a real power of PR. Line is injecting PR real power that is taken by the load. Current flow in the line is I. Impedance of that line is Z. Current flow in the line is I. Impedance of the line is Z. The angle between sending end and receiving end voltages. The angle between sending end and receiving end voltages, delta. Delta is the angle between them. Clear? Same diagram. I will repeat for case 2 also. With some changes, I will discuss both. Same diagram. Taking up for case 2. Case 2. Yeah. First, to draw it quickly. Yeah, please wait for 1 minute. I will come back. Please wait for 1 minute. I will come back and we'll discuss about these two cases. Yeah. So I have resumed audio, video on screen. Are you there? Please kindly raise your hands. Okay, good, good. Listen, listen now, listen. See the case one, case one. First I will set delta at some place in this graph. In this graph, I have two portions. Two portions are two choices here. One, delta less than beta, one choice. Delta greater than beta is the second choice. Two choices. One, delta less than beta. Second one, delta greater than beta. Let's assume delta less than beta point. Look here, all of you. Look here, all of you. Stop writing. Just listen. This is my initial delta. With respect to this is the value of the power to be flown. This is the value of the power flow. Power flow. Clear? This is that initial delta, and that's the value of the power flow. Next thing, listen. At this present operating point, at this present power flow condition, load was increased. Load demand was increased. Load demand was increased. See, all of you, please kindly tell me, after the load was increased, what will happen immediately? What we can expect immediately? After the load was increased, what will happen immediately, or what will change? What will change quickly? Tell me, please. Current will change. Yes or no? After adding load, current will increase. Huh? After adding delta increment and all, we'll discuss. Just think in a very basic way, Dinesh. Dinesh, please kindly think in a very basic way. Okay? As a layman, just if I switch on some load, I do expect that current drawn from the supply is going to be increased. That's it. Look here. Current increased. Because of the current increment, what will happen to voltage drop in the line? Because of the current increment, what will happen to voltage drop in the line? I into Z. Tell me, please. Quick. Increases. I into Z increases. Okay. Whenever the drop is increasing, you see in the short transmission line, the angle between VS and VR, decided by this drop only, na? Angle between VS and VR decided by this drop only. So obviously that angle between VS VR will increase. So I can say delta is going to be increased now. Delta is going to be increased. All of you understood this concept, what I have mentioned. Very simple concept. I didn't said anything directly. Just load increased, current will increase in the line. Voltage drop increased because of voltage drop increment from phasor diagram. That angle between VS and VR will increase. Delta is increasing. Because of the delta increment, if you look into this power angle curve, because of this delta increment like this, obviously electrical power injected also increasing. Okay, electrical power injected also increasing, we can say. So this electrical power injected is increasing means that increment is going to meet the load demand. So obviously, whatever the change you have made for the load, that is accepted by the system, and it is injecting that real power injection. That is safe. System is safe. Will you accept it? Yes or no? Yeah, simple, Shiva. I will explain in the next case also. Just see this, what I am saying. In the second case, delta, I will spot it for delta greater than beta location. I am spotting the delta at this place. This is the initial delta. With respect to that initial delta, this is the amount of the power. This is the initial delta, and this is the amount of the power. Listen, please. Now, look, all of you. Same thing I am repeating. Same thing. Load increased. What will happen? Current increases. What will happen? Voltage drop increasing. Voltage drop is increased. what will happen? Delta increases because angle between VSVR is increasing. Because of this delta increment from the curve, because of the delta increment like this, what is happening to the PR? What is happening to the PR value? That is decreasing. PR value was decreasing, we can see. PR value decreasing. And it is unable to meet the load demand. If it's unable to meet the load demand. All of you getting this point? Right? So I can say, in the first case of delta, even though the load is getting increased, the system is responding. The system is responding positively, and it is injecting more amount of real power. But whereas in the second location of delta, if the load is getting increased, the system is unable to meet the load demand. Not only that, it is decreasing its real power injection. So in the first case, we will say system is stable. Second case, we are going to say the system is unstable. This is the basic meaning of system stable and unstable. System stable and unstable. How delta changes with increase? Many times I said, Vishnu, again you are asking me same. You go through the short transmission line phasor diagram. In the short transmission line phasor diagram, we clearly mentioned that the angle between Vs and Vr is decided by I into Z phasor. I into Z phasor. Voltage drop phasor. Okay. Voltage drop is increasing means obviously angle difference is going to be increased. Good. So in the first case, we will say that the system is stable. System is stable. And whereas in the second case, I will say that the system is unstable. System is unstable. Now, if you go with the equations, let's say, if you are going with equations, first case, first and second cases, both. Listen, all of you, stop writing. Listen. Both cases, P load increasing. Both cases, delta is increasing. But in first case, according to the delta increment, PR is increasing. But in second case, according to delta increment, PR is decreasing. So if you take up delta PR by delta, if that is positive, then the system is stable. If delta positive, delta PR is also positive, then the ratio is positive, system is stable. So I'll write if you want. Delta PR is positive as well as delta is also positive. Therefore, you can say delta PR by delta is a positive value. But here you see, delta is positive, but delta PR is negative. Now, if you take delta PR by delta, that value was negative. Negative. But the change what we are making now is negligibly small. Delta variation is negligibly small. If that's the case, you can call this like dPR by d delta positive or greater than 0. System is stable. And here, dPR by d delta less than 0. System is unstable. Less than 0, system is unstable. What do you mean by the dPR by d delta? What do you mean by the dPR by d delta? Yeah. What do you mean by dPR by d delta? Slope of the power angle curve. So if you are lying, on the positive slope region of the power angle curve, then you can say that the system is stable. If you are lying in the negative slope region of the power angle curve, the system will be unstable. Simple. So in this zone, dPR by d delta is greater than 0 and the system will be stable. System will be stable. Whereas in the other region, we have a negative slope region here, negative slope region, where dPr by d delta value was less than 0, and in this region it will be unstable. Okay, and at this point, this point, dPr by d delta equals to 0. At that point, we can say the system is either marginally stable or marginally unstable. Marginally stable or marginally unstable. Okay, so I will write that also. Right. So if dPr by d delta is equal to 0, system is either marginally stable or marginally unstable. Or marginally unstable. Marginally stable or marginally unstable. Clear? So for if you think about the angles now, slope is positive for an angle delta less than beta. Slope is negative for an angle delta greater than beta. Delta less than beta, slope is positive. Delta greater than beta, slope is negative. Delta equals to beta, we are having this condition of marginally stable or marginally unstable. Delta equals to beta, we have a condition of marginally stable or marginally unstable. And this delta equals to beta, we are going to call as stability angle. Stability. Stability angle. Done? I think all of you getting this? Yeah. So we'll stop at this point. We'll be continuing in day after tomorrow. Tomorrow we don't have T&D class. We don't have T&D class. You have as usual evening class. Evening class will be there. Evening class will be there. You don't have T&D class. Okay. Day after tomorrow we'll continue with this. Day after tomorrow we'll continue with this. Yeah. Please kindly listen this announcement what I'm making. Listen this announcement what I'm making. Look here. If anybody joined for offline, classes, right? You don't get link. You don't get link once if the offline classes got opened. If you want to convert from offline to online, you have to put a request to our institute. Okay? To convert from offline to online. Offline to online. You need to put a request to the management. Request. Okay? Again, as it is, if you want to convert from online to offline also, you have to put a request. Yeah, all of you getting what I'm saying you?
Sir, one more announcement, sir.
Yeah, sure.
Sir, presently going on 2 subjects, na? After these 2 subjects complete, these 2 subjects complete.
After completion of these 2 subjects only, offline will open.
Will be start. Yes, yes.
After completion of these running subjects, T&D and power electronics, then only offline classes will be started.
Yes.
Okay. Sir. So anyhow, you will be getting an intimation by 2 or 3 days gap. So by that way, you can apply. If you want to convert from offline to online, you have to apply within that time. Yeah.
Yes, sir. Okay.
So it will be same, Pratik. Online, offline, it will be same. There is no difference. In faculty, you are asking me, that will be same. Mostly, we are expecting this to complete by 8th or 9th maximum. 8th or 9th, both subjects. By 8th or 9th, we are mostly completing this. Okay.
Sir, Pune not yet decided, sir. That will be.
Pune not yet decided till now. Pune not yet decided regarding the offline. So you have to continue in the online. Sir,
Yes,
for
announcement.
online to offline, extra charges need to pay. Yes, you please inquire about it, Shiv Prasad. Shiv Prasad, please inquire about it. You put a mail, they will reply you regarding it. Only in Hyderabad. Only in
Yes, sir.
Hyderabad, offline is getting opened. Not in every center. Only in Hyderabad. Is it correct, Sheshu?
Yes, sir. Yes, sir. Exactly.
Okay. Yeah. It will be same. I said faculty will be same. There is no difference. If you have any doubts, ask me now. So I'm making all the hands low. Please kindly raise your hands quickly. Pranjali.
Yes, hello sir. Only one doubt.
Yeah,
132 slide number 132.
Okay.
Sir, only sir, this graph after we subtract that second term cos beta minus alpha, after that we will get the next graph. Is that right, sir?
Yes. See, red color graph is indicating only first term.
Yes, sir.
Okay. Then you have to subtract this term, na?
Yes, sir.
After subtracting that red color graph will shift down.
Yes, sir.
Whenever it is shifting down, it may fall above the origin or below the origin. Both chances
Yes.
are there.
Yes.
So I have considered it above the origin.
Okay. Okay,
This is
sir.
a resultant graph. Resultant graph.
Okay, sir. Okay,
Okay.
got it, sir.
Yeah.
Yes. Thank you, sir.
Vishnu.
Sir, my doubts are, so one is this, whenever we learned about this capacitance in the last shunt admittance, no, sir.
What is that? Please tell me.
That capacitance in the, like in the line, we consider that capacitance, that is as shunt admittance, no, sir.
Yeah.
Sir, previously in that previous unit, we learned that the capacitance between lines only exists, not to the ground. So actually, are we converting these?
That's neutral. That's what I said many times. No, delta connected to star.
That star you connect, and that capacitance is what we consider here.
That's it. All the time that capacitance only, Vishnu.
Okay, sir.
It's not to ground. It's to neutral.
Okay, sir. Okay, sir.
Even though you have a conductor to ground capacitance, that you have to add it.
Okay, since both
Because
are in
both
parallel.
will come in parallel, no? That you have to add it.
Okay, sir. And sir, a major doubt is regarding this. Like from previous class also you mentioned that this V phase is V line by √3 in the case of transmission lines.
Yes.
Sir, is there any mathematical proof or something for that? I tried to derive on my own, but I couldn't get it.
If you have that type of doubt, you better think about the insulators.
Sir?
Insulators. 3 insulators are connected in star.
Okay, sir.
So that is grounded.
Okay.
Tower is grounded.
Okay.
So conductor voltage means conductor to ground.
Okay, sir.
That is the insulator voltage. That will be line to line voltage by √3.
Sir,
because it's like a star load, right?
Okay, okay, sir. For star, like assume like it as a star.
Like that you can understand if you want.
Okay, but there's no written proof for this thing. There's only just understanding point of view, or
yes, that's it.
All right, sir. And sir,
else what you have to do is you connect a star connected load to the transmission line, then you can find out terminal voltages.
Or like you could assume same like this capacitance alone, like converting this delta into star and that voltage.
That also you can assume. If it is a delta connected source, convert it to star.
Star. Okay, all right, sir. That's fine. Sir, 131F.
Yeah.
Sir, in 131F, you mentioned that this load must have a capability of delivering Q. This Q, as in we have generally assumed that it is lagging power, reactive power, or
lagging reactive power only. I will discuss about that in voltage control, Vishnu.
Yes, sir. No,
I don't want to confuse you by saying all the terms at one point.
Okay, sir.
That's why I'm introducing point by point. First, I introduced the reactive power. After that, I discussed about VI conjugate equation. So with a space, I am discussing each and every crucial point.
Okay,
so I will discuss about lagging Q and leading Q also in voltage control.
All right, sir. And sir, last slide that setting of these points delta and beta.
Yeah, tell me.
So this delta and beta, like in the graph you have mentioned the point where this Pmax occurs as delta is greater equal to beta.
Yeah.
But this graph again is with respect to delta again, then how can we set delta greater?
Delta number 0, 1 degree, 2 degree, 3 degree, 4 degree.
Oh,
like
okay,
that,
okay.
right?
At this point is
That is beta is constant, right?
Okay.
It's a number. Numerical, right?
So
Delta is a variable.
Okay. All right, sir. That's it, sir. Thank you, sir.
Yeah. Ramakrishna.
One small doubt, sir.
Tell me.
This one before slide, sir. This
Before slide. Okay.
Sir, why not PR is equal to 0 if we take assumption?
Chances are there.
Assumptions like delta equal to alpha.
Okay. Chances are there. Not delta is 0. First you have to assume.
Okay, sir.
Then you say that VSVR by mod B.
Yes, both are equal.
Both are equal. Then
yes,
you have a chance.
Then,
you have a chance. Yes.
Yeah, that's okay. That's what, sir.
Yeah.
Okay, nothing.
Akshay.
Hello, sir. Just a general doubt, sir. Like when we learned two-port networks, we were told that the convention for current is that both currents would be incoming. So, but in power system, we take it.
We are taking source and load distributions here.
Okay.
There, whatever that second port current injection, they will keep as negative sign in B and C. B and D, I think so.
Oh, okay.
They will show minus sign in B and D, na?
Okay, so we
I
are
am
just
moving that minus sign to current.
current.
So
Okay, I'm taking it outside.
That is going outward.
Okay, sir. Yes, sir. Got it. Thank you, sir. Yeah.
Balviknesh.
Sir, in this curve alone, sir.
Hmm?
In this page alone, sir, I have done.
Yeah. Tell me.
Sir, this is first the blue dotted line indicates the cos delta, sir.
Cos delta.
Then we are shifting it by beta times. Beta
times.
angle.
Okay.
Okay. Next page you have drawn the exact power angle curve. That
by
is
subtracting this term.
Okay, sir. That's one, sir.
After subtracting only I have drawn it.
Okay, sir. And another doubt in 115F, sir. 115.
Yeah.
Sir, here R equal to mod Z into cos Y, sir. Is this cos Y represent the power factor or it's the angle between
impedance angle?
Impedance angle. It is, we can't able to find the power factor, no, sir.
If it is alone the load you have, that cos phi itself is power factor.
Sorry, sir, can't understand. How, sir?
If this is a load you have, if this is a load for which you want to find power factor, cos phi is power factor, right?
For load, we can find the power factor by this formula.
By using R by mod Z. But for line, you should not say.
Okay, sir. Sir, and another doubt, sir.
For line, you should
yes,
not
sir.
say R by mod Z is a power factor.
Okay, sir.
But for load, you can say load impedance, R by mod Z is a power factor of load.
Sir, and another doubt, sir. When the capacitance is connected in shunt, sometimes we represent minus J2000, minus J2000. When we are representing it as an admittance, we need to include minus, sir.
No, actually, impedance of capacitor will come with a minus J symbol.
Okay, sir.
Why it is coming with minus J means that you should study in networks.
Okay, sir.
So because of the phase angle difference and all, you use keep that minus J symbol for it.
Okay, sir.
Okay, so
sir,
inductor impedance will be with less J symbol. Capacitor impedance will be with minus J symbol.
Okay, if capacitor impedance means either it is admittance or impedance, irrespective of that, we need to mention it minus.
Impedance is minus J.
Okay,
admittance, if you are doing 1 by minus J, you will get, right?
Yes, sir.
It will come to plus J.
Yeah, that only I'm asking, sir. And because on day before yesterday, one problem got done, that 2K, 4K, that problem,
okay.
sir.
That's okay.
There we are representing as admittance or impedance, sir.
That is impedance,
minus,
right? That is impedance.
But you said minus means only useful for admittance.
What is it?
You said minus we will use only when it is admittance to represent.
Listen, capacitor impedance will be minus J symbol.
Okay, sir.
Capacitor admittance will be plus J symbol.
Okay, sir.
Then what's your doubt?
Okay, sir. Now, okay, sir. Now clear, sir.
Yeah, fine.
Thank you, sir.
Naveen Sai.
Sir, in the slide number around 97 something, sir. X by R values, X by R ratios.
Okay.
Here, sir. If the voltage is high, generally we in first chapter we studied the cross section
That's
area
for
is,
equal power ratings. That's why I'm
okay, sir.
mentioning here clearly unequal power ratings.
Okay, for constant power only that condition is valid.
That condition, the earlier condition is valid, but here it's for unequal power ratings. Practical lines will have higher power ratings for higher voltage lines generally. If you see
that means
outside, listen,
Yes.
you see outside 11 kV wire and a low voltage wire.
Sir,
Which conductor size looks to be bigger?
11 kV.
Because that's having higher power rating compared to 400 volts.
Okay, sir.
Okay.
That's it, sir. Okay.
Spain.
Yes, sir.
Yeah, let me Spain.
Yes, sir. Good afternoon. Sir, one doubt is that when we are representing the medium transmission line, we are in many in all cases nearly we are saying that the AD minus BC is not equals to 1.
Where it's not equals to 1?
That is sending end capacitor model.
It's coming. No, just check once.
In some cases,
Sending end capacitor model ABCD parameters 1 ZY 1 plus ZY.
that is AD minus BC. In some cases,
is 1.
A is equals to D, symmetrical.
Which model you are asking me?
Yes, sir. I'm asking, sir, general case actually means in a long transmission line we are
Long
seeing
transmission line case parameter A cos H gamma L.
we see that this is there is symmetrical as well as reciprocating. Can we conclude for the physical meaning of that when we are converting it to medium transmission line, that error is generating? AD minus BC is not equals to 1 means some error.
Definitely AD minus BC will come as 1. Oh, you are saying approximate.
Means
in the approximate we may not get, but it will be close to 1.
Physical significance is there? Means
physical significance means we don't have any source. That's the meaning of reciprocal network.
Okay.
Inside the network, you don't have any source. Source will exist only at the ports.
Okay.
That's the meaning.
If sources are
present, you don't get AD minus BC equals to 1.
Okay.
Yeah.
Okay. Means in the long transmission line, we are getting AD minus BC is equals to 1.
You are getting right?
We are getting means in that case we are trying to exact analysis.
Yes.
But in a medium transmission line, we are not at the exact analysis.
But still we are getting passive network.
Okay.
But still AD minus BC equals to 1, even for medium lines.
Yes. Okay.
Okay.
Yes.
Any other doubt you have, Swain?
No.
Tambe.
Good afternoon, sir.
Good afternoon, Tambe. Tell me.
Sir, 106 slide.
Okay.
106. Example, sir. Next
example.
Slide. Next slide.
This one.
This.
Please read. This one.
This, sir. How we calculated, sir? They
have given it is nominal voltage, right? They have given nominal voltage in the problem. Rated voltage 220.
Okay, sir.
Yeah. Right. Shiva.
So good afternoon, sir.
Good afternoon. Tell me, Shiva.
Sir, 133.
Tell me.
No, sir, 133. So here we are like delta is equal to the input power factor angle. Is it so, sir? Like when we
no. What is it input power factor angle?
No, sir. While referring it to the phasor diagram of short transmission.
Okay. Delta is equals to pi s minus pi r. If you are referring to short transmission line.
What is phi s minus phi r?
Phi s minus pi r.
okay, sir. And then in 88F, sir.
Tell me.
Sir, here I don't understand how it is independent of length of lines.
See, you multiply with 100 numerator and denominator. It will be cancelled, right?
Okay.
50 kilometer length or 100 kilometer length, the ratio will be remains constant. Na?
Yes, sir.
That length will be cancelled out. That's
So, and then second one, it mainly depends on the radius of conductor.
because this Z and Y consisting L and C, inductance and capacitance.
Okay, sir.
Inductance and capacitance values mainly depends on size of conductor and spacing between conductors.
Okay, sir.
Okay.
Yes, sir. So then last one, sir. How you told a reason like for representing VR and IR in phasors. Could you please explain it one more time?
VR and IR phasors, sir.
Yes, sir. Like we are taking it as a phasor while representing ABCD parameters, right, sir?
Oh, I didn't get you exactly what you are
sir,
saying.
In ABCD parameters, we are representing the supply voltage and all the stuffs in phasors, right, sir? Like VS
Okay.
phasor.
Okay.
So
Okay.
you told the reason like you told the reason why we are taking it in phasors.
Because those are sinusoidal signals. That's it.
Okay, sir. But you said something about the angles between them.
No, I didn't say
like
anything.
Okay, sir. Let me watch it in record.
You review once. Review and ask me if you have anything.
Yes, sir. Okay, sir.
Any other
That's
doubt
it.
you have, Shiva?
That's it. Thank you.
Okay. Shravan Kumar.
Yes, sir. Hello, sir.
Tell me, Shravan Kumar.
Sir, I missed that. What is the definition of beta, sir?
Beta is angle of parameter B.
Angle of?
Parameter B.
Okay, sir. Delta means load angle, sir.
Angular difference between sending end voltage and receiving end voltage.
Like that beta means?
Beta is impedance angle. Angle of parameter B we are saying.
Okay, okay, sir. Like that Z has some...
Z has some angle, right? That's it. That's the angle taken for beta also. So B also.
B means parallel impedance, sir. Impedance in
Series
parallel.
impedance. Series impedance of transmission line approximately.
Okay, thank you.
Anil Kumar.
Sir, good afternoon, sir.
Good afternoon, Anil. Tell me, Anil.
Sir, we have already discussed that reactive power now, sir. For positive cycle, it flows from load to source, and negative cycle, it flows from load to source. What are the purpose of flowing, sir, reactive power? Is there any disturbance in the system?
Whenever you keep that inductor and capacitor in the circuit, those will be continuously storing the energy and releasing the energy back.
This is the main idea.
That's a natural thing which is happening in the system.
Okay, sir.
Because of that, definitely there is a circulation of the reactive energy.
Okay, sir.
Yeah.
Thank you.
That's it, Anil. Any other doubt here?
No, sir. Thank you, sir.
Yeah.
Sir, 1 minute, sir. I have one small doubt, sir.
Tell me, Balavinkesh.
Sir, for delta, can we represent as delta equal to phi s minus phi r, sir?
That you can do only for short lines.
For medium and long, we should not do like that.
No, you should not do like that. If the shunt element is neglected, you can do for anything.
Okay, sir.
Okay. The shunt element is not there. Only series element is there in your circuit. Then you can do it.
Sir, on the term you said for steady state, you need to do by the lumped model, sir.
Yeah.
If the question is they are asking the steady state load flow analysis, can we do with the exact model, sir? What we have discussed today.
There we have to go with equivalent pi and equivalent t.
Okay, sir. That is the exact one.
That we'll discuss. We have found only ABCD of distributed model.
Okay, sir.
That we have not converted into lumped.
Okay, sir.
That we'll discuss after a little time.
Okay, sir. Okay. Thank you, sir.
Okay, yeah. Soundarya.
Hello, sir.
Tell me, Soundarya.
X by R ratio 400 kV greater than X by R ratio in 200 kV, na, sir? One transmission line we are taking now 150 MVA. How will come to 3 lines, sir?
No, 150 MVA power is getting divided between 3 lines.
Sir, please once explain, sir.
450 MVA we have taken here. That 450 MVA getting divided between 3 lines.
How, sir?
Power division only we are talking, Soundarya.
Yes, sir.
Power is getting divided between 3 lines because of their own demand.
Okay, sir.
Like simple like KCL you can apply if you want.
Okay, sir. Okay.
KCL you can apply.
Okay, thank you, sir.
That's it.
Yes, sir.
Pallavi. Pallavi, do you have any doubt? Pallavi? Anybody having doubts? Please raise your hands. Pallavi, do you have any doubt? Salman Khan.
Hello, good afternoon, sir.
Tell me, Salman Khan.
Sir, when line divides into the example in this diagram 3 parts, then its reactance also reduces, na, sir?
Reactance will be same. We said GMD by GMR will decide it.
Yeah, GMD by GMR will be.
Ln of GMD by GMR will be more or less same, no? Even though GMD by GMR is changing, natural logarithm of GMD by GMR will be more or less same, right?
Right, sir. Right. Okay, sir. That's it. Thank you.
Jessica.
Hello, sir.
Tell me, Jessica.
Sir, I did not get why we are representing VS, VR, all those things in phasor form for this ABC.
Sinusoidal signals, right? Those are sinusoidal signals. To identify the magnitude and angle, we are representing them as phasors.
Okay, sir.
Wherever I write VS, it will be having some magnitude and associated angle.
Okay, sir.
If I want to write magnitude, I will keep modulus definitely.
Sir.
If I don't keep modulus, it will be having an angle as well as magnitude.
Okay.
Okay. Sometimes I will write VS bar. That's also okay.
Okay. So if it is like
to stress or to make you remember as a phasor, I will keep VS bar sometimes. Even though I didn't keep bar, it's having a magnitude and angle. Okay.
Okay, sir. So it is because it is a sinusoidal.
Sinusoidal means we have a magnitude as well as a phasor, right? Phase angle.
Sir.
Yeah.
Okay, sir. Thank you, sir.
That's it. Okay.
Yes.
So anybody have doubts?
Sir.
Tell me, Anil.
Sir, in 74 slide.
74,
Yes, sir.
Okay. Tell me.
Sir, in this slide, you have to tell how to remember that matrix easily.
So A and B are okay. 1 plus ZY by 2 that you have to remember.
Yes, sir.
If the total impedance is kept at only one place, B equals to Z.
Yes, sir.
In the earlier case, total admittance is at only one place, so C equals to Y.
C equal to Y. Yes, sir.
C equal to Y.
Okay, sir. Okay.
B representing series impedance means it will start with Z into some factor.
Okay, sir.
In case of this, C is representing shunt admittance means Y into some factor.
Okay, sir.
1 plus ZY by 4, you would remember 1 plus ZY by 4 multiplication.
Okay, sir.
If it's a nominal pi, B equals to Z.
Okay.
Then C will come automatically Y into 1 plus ZY by 4.
Okay, sir.
Okay?
Yes, sir. Okay.
Yeah.
Thank you.
Pratyusha.
Sir, why we always discuss about single phase and three phase systems? Isn't there any two phase?
Actually, we are having only 3 phase systems.
Okay, sir.
That we are doing in a per phase manner analysis.
So two phase system is not existing anyway.
2 phase system is not existing because of its cost as well as not having much power transfer capacity.
Okay, thank you, sir.
Yeah. Any more doubts you have? Please raise your hands, else we can close. Any more doubts? If you don't have doubt, you can leave. Don't have doubt, you can leave. Karthik.
Sir, am I audible?
Yeah, tell me, Karthik.
సార్ మనం ఇప్పుడు పవర్ ట్రాన్స్ఫర్ ఇప్పుడు ట్రాన్స్మిషన్ లైన్స్ ఉన్నప్పుడు ఏసీ ట్రాన్స్మిషన్ లైన్ డీసీ ట్రాన్స్మిషన్ ఉంటాయి కదా సార్.
ఎస్
సార్ ఇప్పుడు మామూలుగా ఏసీ ట్రాన్స్మిషన్ కన్నా డీసీ ట్రాన్స్మిషన్ లాస్ తక్కువ ఉంటాయి కదా సార్.
ఎస్ కరెక్ట్.
మరి ఏసీ ట్రాన్స్మిషన్ ఎందుకు కన్సిడర్ చేస్తారు సార్?
Because of cost effective.
ఓకే సార్.
Transformer action is not there in DC. That's the main disadvantage of DC. Transformer action is not there, no.
Yes, sir.
You can't step up or step down the voltages.
ఓకే సార్.
That's the main problem.
ఇది ఎప్పుడు వచ్చింది సార్ డౌట్?
Okay.
థ్యాంక్ యూ సార్.
Yeah. So any more doubts? If you don't have doubt, you can leave. I'm closing the session. Ronald. So I think nobody's having a doubt. Thank you.